Yeah,
I mean,
So I will be one of our twins.
Oh, getting person.
All right. And now we're unmuted on Teams. So hi Teams people, virtual people, so sorry about that. I'm Sarah LaLiberty, Marketing Chair. Welcome, and we encourage your interactive participation. All right, so to get started, just a few housekeeping items. I did a quick intro of me and Mackenzie. You will have access to this area as long as you are wearing your Bosch badge and someone lets you in. This is actually a restricted area, so you need to be badged in. So we appreciate your consideration. If you need anything, find someone from Bosch, find me or Mackenzie, and we'll help you out. There are some rooms for the breakout sessions this afternoon that are going to be across the hall, and we'll escort you over there. Those you will not need the badge access, so it'll be easy for you to leave. It's harder for you to come back in, but we've got you taken care of. So as long as you're wearing your badge, someone around will be able to help you. There are restrooms in the hallway, and there's also restrooms in the front lobby when you came in. If anybody has any questions, just stop any Bosch person or us, and we'll be able to guide you. Over the course of the day, we have multiple opportunities. You shouldn't be hungry or thirsty. So we have juice and flavored waters and different beverages over in the corner, coffee and tea, and then we have pastry set up this morning. We'll have a morning coffee break, we'll have a full catered lunch, and then this afternoon we have some fun desserts to share with you all. If you find you need anything, you have any dietary restrictions, please again, reach out and we'll help you. Everybody parked, I hope. So if anybody has any questions about where they parked or if they need additional help, let us know. If tomorrow when you come in, the front parking lot is full, we have an overflow lot around the corner, and all you need to do is come back to that front entrance where you came in and we'll let you in. On the table is instructions about the Wi-Fi, and I've also put it up here. So please, everyone, feel free to access the guest network. The security key is right here, and you can type that in, and you will need to accept the user agreement in order to jump online. All the presentations are available online, so if you want to call them up and follow along, you certainly can. So we have an action-packed couple of days. We put together a great schedule for you. We're really excited about the wonderful speakers that are joining us. Again, this schedule is available online, but a preview of it this morning and this afternoon. The colored blocks are the breakout working groups. So think about if you want to join software portability or cybersecurity or benchmarking. And we welcome, during this conference, we welcome people to join us that are non-members for these breakouts. Get a taste of what we do, and Stephen will talk more about that afterwards, and we can go from there. All right. So the first thing I need to do is welcome our chair of the board of directors of AVCC. Elizabeth Cow joins us from Bosch. And today she will be talking about the organization, welcoming you all here to her company, and she just comes with a wealth of experience. So I'm really excited to introduce Elizabeth to you. So Elizabeth.
Thank you. Good morning. I'm so happy to see everybody. Welcome to our 2024 member meeting. So we have our members here as well as we have guests, because we do want to increase our membership and we want to be able to participate as an industry in ADAS and autonomous vehicle compute and push ourselves into that future. So what do we need to do to get to that autonomous ADAS and software-defined world? So I broken it into 5 pieces here, and we're going to make this an interactive portion. So folks online, also get ready with your raise your hand button. Okay, so the first thing that I see on our journey towards ADAS, autonomous and software-defined vehicle is on that compute side. To really have that powerful enough compute that we can do the things that we want to. We've seen automotive compute go through that transition from something on the order of a smartphone to a tablet, to a gaming console, as your kids probably know, a PC and a workstation. So we do believe that this has to sit on that strong foundation of compute. So now we're going to do the interactive portion, which is a little bit of retrospective on what we've been doing at AVCC to deliver value and how you guys are participating, but also how we continue to participate into the future, including this afternoon and next afternoon as we have several working groups. All right, so things that we have delivered in the last 12 months include our automotive benchmark. We had another technical report that we published, as well as this time last year, we signed an agreement, a partnership with ML Commons to work on ML Perf automotive benchmark. So raise your hands on people that have been participating or joined meetings with automotive benchmark, ML Perf automotive benchmark. Raise your hands, keep them raised. Who have gone to the meetings, who have gone to the webinars, who have participated in the paper. I see some more. Don't be shy, keep your hands raised. And people who are now starting on that newest piece, which is the pre-silicon benchmarking. All right, thank you. And I believe that Stephen Miller, usually Casper and James Goal are leading that, but Casper, we're very happy for him. He's on paternity leave. We miss him terribly here. The next piece, hardware software abstraction. So we believe that there is room for more standardized API and that there's that room for industry collaboration on how to standardize. So usually that's led by Rajive. So raise your hand, Rajive, keep it raised. Who else has been participating on software portability? Who have gone to the webinars? Who have read Rajive's blogs? Who have seen Rajive speaking at different conferences as well? Okay. So then this afternoon, Rajive will also be doing a work group as well. Software factory. So we know that we have to have that incredibly efficient DevOps and CI/CD, that continuous integration, continuous development, for us to bring that software in for autonomous and ADAS and software-defined vehicle. It's in a very, very different clock speed, as well as this software, because many of us from automotive know it's got to last 10, 15, 30 years. Part of that is also on our cybersecurity and our security structures as well to last into that time frame. So the cybersecurity led by Andrew Jones, keep your hand raised because we also have the next one that we just launched, which is AI cybersecurity. Jonathan, I don't see him at the moment. Keep your hand raised if you've been participating in that paper, the presentations, the webinar, or the next one, AI cybersecurity, or if you just want to. Bob Castor, your hand better be raised. Okay, thank you. So that will be another group, working group. I mean, I saw your hand raised over there. That'll be another work group that we'll have later on. Okay, to put it all together, we don't necessarily know the exact killer app that's coming, but we need to make space on our compute side for that future, such that we have enough headroom on our compute side. We have the software factory that can deliver, and then we need the business model to deliver that return on investment. We call it TCO, but Neil will keep reminding me, no, we should call it return on investment. What are those new methods that our industry can capture rents, licenses, subscription, one-time, pay for use? So raise your hands if you've been working with Volker on total cost of ownership. Either his blogs, Volker, raise your hand. He'll be also having some work groups as well. So we'll be doing some afterwards. It's really important what we need from you. And now at this point, every person should be raising their hand. We need you to fill in these surveys. Help us understand as an industry total cost of ownership. This started when we had 2 years ago a member meeting in Munich, and it became obvious like our mental models on TCO was completely different on total cost of ownership. And we felt like most purchasing traditionally is keep it really tight, down to the dollar, down to the dime, down to the penny. But that may not work as well when we're looking at ADAS, autonomous, and software-defined vehicle markets where we need some headroom to be able to bring in these next features. And the last one I have then is organization. So organization, many companies are looking at a difference between hardware and software. They're trying to organize such that we can deliver these software defined vehicles far into the future, but have that agileness right now in delivering that software factory. But what we are finding is that things are delayed. We believe that this push towards central compute in many cases is being delayed right now. So there must be something that we need to work together as an industry, collaborate. Of course, we'd like to go it on our own, but when we get stuck, that's when we need that industry collaboration. And so that's why we're here together as AVCC. So raise your hands if you guys are have been going to member meetings. Well, I guess it doesn't count because all of you guys are here. But meeting with Neil Banerjee, as well as John Carentis on our outreach. Folks doing outreach, maybe then you've even helped other people in your industry come in. And do want to recognize two new members. We see AMD, Paul Zarati is here, as well as Motive Power also joined us very recently. So we do expect that now that the pandemic is over, we are trying to build that momentum with AVCC. We're so glad that you're here, and we hope that you continue to participate because the industry consortium is only as good as what the members put in. And with that, I will give it back to Sarah. Thank you.
All right, thank you, Elizabeth. So we're really excited to have everyone here. And without further ado, I'm happy to announce today's keynote. So we want to welcome Ole Godbersen to the stage. Ole is from Bosch, our host company here, and he has a wealth of industry knowledge, specifically in our area. So he is going to be talking about the future and the challenges that we face and how we're going to overcome them. So Ole, welcome to the stage.
So thanks a lot for hosting me. It's a pleasure. It's an honor for me to be here today, even if I'm a bit tired because I left yesterday. So if I fall asleep during my speech, just what do I want to talk today? Basically, Elizabeth mentioned some of the basic points we are needing for software-defined vehicle, we are needing for ADAS in the future, and one is, of course, compute. It's not only power, but it's compute now. The other one is hardware-software abstraction. And I think we all agree that we are in a time of change. Everything is delayed, everything is developing a little bit different than in the past. And that's what I want to talk about today. I want to talk about change and about the vision. Yeah? About the vision, how chiplets, meaning these small dice, yeah, can transform automotive compute through collaboration within the industry. Yes. Basically, if we are talking about change, I would like to start with vision first. And let's imagine what we have as vision, or what we're trying to develop as vision in the past. What we have in mind is we want to create a real open ecosystem where we can mix and match chiplets to create dies serving our automotive needs. That's the vision we are having in our mind. And that's a collaborative vision. That's not a vision Bosch wants to do. As on their own, that's not possible. What we really want to achieve is that we have a multitude of competitive players providing these small dies designed for the need, having the necessary software on board, also maybe in touch with you guys talking about hardware software abstraction, having the tools available to design these chiplets at the IP. Yeah? And we think such an ecosystem will come with strong benefits and a strong value proposition. Of course, it will enable single socket centralization in the future. This is what we're striving for. It will achieve, or let us achieve, real flexibility and scalability for our computation SoCs. It will allow us to tailor systems according to our needs, maybe just selecting the newest AI accelerator, which is fitting best for our transformer. And we can even design the chips to really support the software needs of automotive. This is new. In the past, we took over the designs from other industries, added the additional features which we needed for automotive, but it was somehow a mixture. Now we can really drive and design these chiplets. And of course, chiplets means multiple factors, heterogeneous integration, and this can strengthen the resilience of the supply chain. But that's the vision. Yeah? Keep it in mind. And what I now will do is guide you through how we develop this vision and what our rationale behind is. Let's start what we see, what has happened. And I think all of you are aware. We are coming from decentralized architectures. Yeah? Here it's depicted with these three central computers, one for the real-time parts, yeah, maybe hosting an MCU, maybe an RX for NVIDIA, as a core, one for the ADAS function, yeah? As a control unit, one for the infotainment. That's what we see in most of the cars now today. We also see the first advances into shared housing solutions, where we just put several SoCs on one board, on one PCB, yeah, which comes with some advantages, of course, but still still not leverages everything we can get. And what we are foreseeing in the future is the real centralization on one single SoC, meaning hosting different software functionality on one single SoC and making this SoC as scalable as possible to serve the different performance classes which are necessary. Meaning this should be, in an ideal world, the optimal solution because it gives us the highest cost reduction potential. We all know this. It gives us the possibility to optimize the performance and to optimize the utilization of the performance. It minimizes, of course, power demands and dense packaging. And we hopefully can use a lot of synergies. So that's the vision. Yeah, that's the idea where we're leading from. And at the moment, we are standing as an automotive industry in front of a dilemma. We call it the automotive compute dilemma. On the one hand side, you see the increasing performance demands. We are now talking about thousands of TOPS, and TOPS is just one benchmark. We are talking about chips which will tremendously increase in R&D costs. I'm not sure who knows what such a chip is cost in R&D. If you do a tape out or a design in 5 or 7 nanometer, you're easily just for R&D going up to 500 million. Yeah, just R&D costs. So they will be extremely expensive to develop. Yeah. And of course, in automotive, we're having the issue of having not a really fast growing market, unfortunately. Yeah, it's pretty leveled. Yeah, we're having roughly 100 million cars, including trucks, sold each and every year. So it's a limited market. Yeah. And increasing performance demands combined with huge R&D costs for these chips in a leveled market, it's obviously a problem, and it will obviously cause us that we only have a few. On the other hand, if we look into the chips from the OEM Tier 1 perspective, I think we're all aware that we are having significant pain points at the moment with the available solution. We don't see chips serving our needs for scalability through the different performance classes across use cases. And for all OEMs, they are obviously having different needs. Partially, they have an insufficient fit for automotive requirements. We always have to deal with too-less memory for ASLD, too long boot times, things like that. There's limited possibilities for all of us, OEMs as well as tier ones, to influence the designs towards the automotive needs. Of course, if we're looking at the chips right now, there's uncertainty in the long-term availability. Passenger cars, 10 years, and if I look into the truck area, commercial vehicles, 15, 25. Long-term availability, I'm not sure if we can have the chips available right now for the next 25 years. And an additional thing, what we also experience is high switching costs. If you have to switch from one provider to the other, there's always a huge effort attached. Yeah? Bringing your software, porting your software, migrating your software, bringing the chip up, validating everything. This is kind of a real pain point in the automotive industry. And that's in combination what we call the automotive. And we see a potential solution. And the potential solution from our perspective is chiplets. Is everybody aware what chiplets are? Or should I explain something about it? Maybe I do it too quickly. What are chiplets? Chiplet is basically the idea of slicing a single die in smaller pieces and packaging it back together. The reason why the industry is doing this is basically defect density on a silicon wafer. Yeah? If your chip is too huge, defect density will cause you a lot of yield, a lower yield, and this will create a lot of cost, and chiplets will be a solution to it. So chiplet is a technology which is used. Yeah? Paul can tell us a lot more about it, of course. Yeah? You're having this in other industries already in series. And it will...
If you don't mind, can I contribute why chiplet is? So a lot of folks in the computer industry discovered that on one single die with a high density, many of the functions don't need that much. So by having bonding technologies, you can have some chiplets with lower density or older, lower the cost, and is still doing the job. And you can have another chiplet, smaller size, smaller cost, with higher density or more advanced technology. That way you have the best of both worlds.
That's right. I have not seen so many of these chips, but partially they are there. And right now, yeah, I know Paul is nodding his head. Yeah.
Yeah, I mean, process node, depending on what you're trying to implement, whether it's a processor, whether it's an accelerator, whether it's an AI engine, or in our case, if it's programmable logic, a lot of those perform better on various process nodes. This gives you the ability.
Exactly. Exactly. You can design for need. Yeah? If you don't need the most advanced node, why should we do that? And if we look into wafer prices, it might be a good reason to not go to the most advanced node. Nevertheless, chiplet is a potential solution, as I said. And for the automotive industry, it raises an elemental question, or more than one elemental question. Should we just step aside and watch and see what will happen? How the chiplet-based SoCs will look for us in the future? Or can we use the momentum and really address the automotive needs that we build in future SoCs which are fitting for automotive? And to give a short answer, we think a little. Let me give you some idea how we see the chiplet evolving in the chiplet market at the moment, and also in automotive developing. And let's see it also a little bit time-wise from the left-hand side to the right-hand side. And we gave them some catchy names here. Starting with the homogeneous chiplet. What does it mean with homogeneous chiplet? It's just two dice here, which are both alone functional, densely packaged together. Does it help automotive? I don't think so. It's window closed. Yeah, of course, it gives some reuse of dice. It will give some scalability, limited, yeah, but it won't much help. Yeah? Then we have the heterogeneous closed ecosystems. I think AMD is pretty aware of it. So you slice the dice according to computational needs. You can do heterogeneous scaling with it, which is kind of nice. Yeah, you can scale the computation demands for APUs, you can scale the AI, you can scale whatever, the FPGA if you want. It's more flexible, it's modular, but it's still vendor closed. So we don't have open competition. Then what we also see in the market is a little bit a mixture. It might be the first thing which with an open interface in the market is the hybrid chiplet. Hybrid chiplet from our perspective is usually you have a monolithic die and an open interface attached where you can add a die or an IP taped out, which is not coming from the same supplier. This, of course, gives us the flexibility to integrate new things, to enable innovation here, but it don't have so much with scalability. And it is limited because you cannot heterogeneous scale with the different computation units. So that's the reason why we are thinking we need the both of the best of all worlds. We need open interfaces and the possibility to heterogeneous scale the computation units. At the best, in addition with a complete SoC design which is optimized for automotive and which can be can help us bring our functionality into reality and makes the lives for software developers much easier. And that's what we call heterogeneous open ecosystem. So giving us the best of all worlds, but in an open environment. And we know that this is quite a huge challenge and which cannot be solved easily within the next days. And we have an idea how this can work. Of course, the open ecosystem won't be here tomorrow, and not by end of this decade. This will, to have it stable, this will need ages. This will need maybe 10 years from now to have multiple suppliers. They are all really mix and match. This is not easily achievable, but what we can do is setting the foundation. And the first step. Bringing the necessary partners from the industry together, initiating the market entry together with the authorities, developing these with a limited but strong set of partners. And there are a lot of companies in the room which hopefully will have an interest in and driving the industry alignment. What we need in addition, besides implementing something, is industry alignment and standardization. And that's, I think IMEC is talking tomorrow, right? So, yeah. And we have also, IMEC has started an industry alignment there for the chiplet part, for the hardware part, to create a reference architecture. And we think this is a perfectly well-fitting initiative for them. And we, of course, have joined them. That's the idea how we want to, or how we think it's possible to tackle the chiplet challenge. Let's talk a little bit about how we think chiplets should look like. What you see here is we have not started with a hardware design. What we have started with is what are the demands of the software. If we look into ADAS and infotainment, and to be honest, chiplet won't work for small-sized chips. Chiplet might be cost-efficient when you have die sizes larger than 250, 300 square millimeters. Otherwise, it won't be commercially attractive. But what we did is, or what everybody should do, we should start with the functionality. We should look into what is necessary from a feature perspective to run efficiently the chips on the software, the functionality in hardware. The second step would, of course, be check with all available and with all motivated players of the automotive industry how the KPIs should look like. What is the scalability? What is the input sensor? What is the output sensor? What is the required processing power? What are the required processing types? How many KD maps, just to name something, we need for the APUs? And which performance classes? How many tops we need? How many flops we need? How many gigapixel processing power for the cameras we need? This is something we need to define, and this is something where we need to scale. This is the second thing which is necessary to define the right chip. And of course, as soon as we have something, and we are pretty aware that we need heterogeneous scaling depending on the computation resources, we need to create scalability by defining the chiplets right. Sizing the runtime right, sizing the memory demand right, and defining it and making them real scalable for all use cases and all involved. Of course, commercial viability, I already mentioned it. The enabling software stack, and that's where we're coming back to the hardware software abstraction, is something which we definitely need to have a look into it as an industry altogether to make sure that the software behaves and is abstract enough to make software migration easy. And of course, something which will be addressed also within, hopefully within the RTOs, is the packaging, which needs to be solved for automotive. Can we package the chips in sizes which are necessary to serve maybe in the future level 4 and AAA gaming on a single SoC? Can we package it and can we make it automotive? And we as Bosch, we made up our mind. Yeah? We defined KPI targets from our knowledge. Yeah? We defined an initial requirement set. We defined a proposal how this can look like. We did some digging into commercial viability and identified some technical levels. And I think what we need is, as an industry, a reference SoC design. And of course, the reference system requirements for that. And we need to validate this all together within the mobility industry. We need to define refine the architecture with the semiconductor industry, otherwise we won't have a product. And we have to enable the full ecosystem via standardization. These are the 3 major steps we need to do right now. I already mentioned that we have already made up our mind, and let me give you at least some rough idea of how we see the chiplets. Just as a sketch. Of course, it is far more complex in reality than it's drawn here. Yeah? But how do we see it? As I mentioned, of course, we need to scale in different computation points. We need to scale in APU. We need to scale in GPU, depending on the OEM requirements. We need to have here for AI maybe some customization in the future. There are a lot of innovation ongoing. There are a lot of startups outside there which are not able to build a full-blown SoC, but which are able to build maybe for one or the other OEMs the optimal solution for their AI problems. And what we also see is what we think is really important is to have an what we call, or what we think we should call an automotive base stack. It should encapsulate the automotive demands. It should standardize the system behavior. It should hopefully encapsulate the highest safety levels. Yeah, I do not want to have either D here, here, and here. Yeah, we need to deal with freedom from interference to make sure that we have the possibility to run the different software reports. Yeah, to make sure that we can get through homologation at some point in time. Yeah? And make it without the overhead cost of an hypervisor, at least as far as possible. Yeah? That's the basic idea we're having, of course, with open interfaces to address the need. Let me think about a different aspect here as well. And we think that there's also, besides all these technical hurdles we are seeing, there's also a business challenge. And the business challenge is that chiplets, especially an open ecosystem, will definitely transform the value chain. So if you look at this in the current setup, it's pretty easy. The current setup is you have the OEMs, they are exchanging with the designers, yeah? The SoC designers as the SoC integrators. It's the same companies. We have, of course, somebody who manufactures it here because nobody has the fabs for it. Yeah? And you have Nozat who's doing the packaging, but it's pretty straightforward. Yeah? What we're doing now here is to split the chiplet design into different pieces. And this gives everybody a challenge for a business perspective. Because now somebody needs to take over the sub-architecture, and somebody needs to take over the integrator role. And integrating dies from different vendors is quite new, I think, for everyone. Nobody has ever done this before in the industry. Yeah? So this is also, besides the technical world, as a business challenge. We have to set this up and we have to reach this through. But nevertheless, yeah, we think that chiplets really can transform the value chain, and it comes still with the advantages. Yeah? For the OEMs, they can influence these designs as they will look like. They can select AI, they can say, CPU, maybe I go with ARM, I've seen the ARM, the people here, maybe I will go with the Spice, yeah? Maybe I will go with x86, whatever I want to do. GPU, whatever is suitable. I can maybe also use one part from AI for Europe and the US, for the Western world, and one for China to overcome additional challenges. Nevertheless, the OEMs definitely have a real advantage here. They can define with the industry. The multi-partner setup has also an advantage for all of us. It will create competition. And what does competition usually? Where everybody involved, prices will go down, innovation will go up. That's what usually happens if you have fierce competition, and that's, I think, a good thing. Yeah? Without this, innovation would die. And of course, a new role in the industry, I already mentioned. But nevertheless, this is the business challenge we also have to face. We also have to tackle if we want to make this vision reality. So what do we need for this? And that's coming back to the title of the presentation, collaboration. Collaboration here is key to make this reality. This cannot be just driven by one company. I think IMEC will tell you something similar in their speech. We need the AI embedded innovators. We need the startups who can bring new innovations into the industry. We need the IP vendors to make the IP available, to make die-to-die, to make the cores available for everybody. We need the fabs and the packages on board to manufacture the dies and to package the dies. We need the tooling companies, Siemens, Cadence, Synopsys, to let us design and create virtual environments to make software development easy from the beginning. We need the RTOs, we need the research institutes on board to foresee the next steps to make these pre-competitive available, the necessary technology. We need the software plates. We need, of course, system BSW, hardware abstraction layers. We need middleware, which is suitable for the automotive needs. We need functional software, of course, to prove that everything is working. We need users and integrators. We need tier ones on board to do this. We need OEMs on board to do this. We need somebody who brings an SoC on a PC. We need somebody who brings the software up. We need somebody who brings the SoC up. And we need, of course, the chiplet supplies. And that's one of the key challenges. But if we are all working automotive and semiconductor industry together, we can really make it. So last slide for today, hopefully I'm on it, right? To summarize it, what we really see is that the next years we can transform the automotive industry, especially the compute, through collaboration. Chiplets will be reality in automotive. This will be no question at all. The only question is, can we influence it? We think we should, if chiplets will become reality, we should think chips differently. We should let functional demands drive the SoC design. We we definitely believe in the idea of an open ecosystem, lower the entry barriers, enable competition, allowing tailored solutions. For that, we need the cooperation and we need to collaborate it out. And to be honest, the only thing I can say is let us jointly embrace the challenge and let us make it through. So now, hopefully there are a lot of critical questions because I think there are a lot of parts which are not discovered yet. So feel free.
Thanks. Great presentation. I have a question on the UCIe interfaces that you talked about. Where are we in the evolution and in terms of like implementation and availability and people being able to use those to actually build the
UCIe is available. UCIe is defined in version 1.1. The application outside, there's limited support of older process technologies, of course, at the moment. If you look into it, you see the IPs available for sub 10 nanometers, but not above. So this will limit us a little bit. There might be during the design phase that there needs to be some changes, but we have to be a little bit careful here. I doubt that we should influence UCIe in a way that we add, for example, additional lanes which are automotive specific. Because if we are doing this, then it will be automotive UCIe and not UCIe. So yeah, I think there's some work to do. It's the standard 1.1. Like always, 1.1 means not mature enough usually, at least not for automotive. But I think we're in a good way, and we need to change it. There's a UCIe automotive working group, and hopefully we come out there with some good solutions. But it will need some time, of course, and we need a first implementation from different vendors. That's key in the end. Somebody has to take the first step implementing these die-to-die interfaces, showing that this will work.
And do you feel like the older process technologies can support UCIe?
At least it should, why not? There's at the moment no need from other industries. That's why they're not available. I would say UCIe, if used, will be used in the newer ones right now. Because you don't build chips in 22 nanometer with as in a chiplet technology. I haven't seen this.
You mentioned about the tier one aspect, tier one ecosystem integrators, OEMs. Tier twos are technically highly competent in making chiplets with their own ecosystem of fabs and contracted fabs.
Yeah.
What do you see is the need of a tier one when in perspective of chiplets here? Because tier twos are much more competent, can work with the OEM directly with the requirements.
I'm not really sure if we should talk in the old terms tier one and tier two. If I would say what should be a role of an integrator, I would name it something like tier 1.5. Yeah, it's something in between. You need to have the automotive demands in mind. You need to have the experience in building these chips up on the board. But you also need, of course, the T2 competences. So it's a mixture. I don't think that the integrator role needs to be a tier one.
This is a kind of a follow-on that question. Talk about collaboration, but industry disruptions have losers as well, right? What challenges do you see in that area in where the ecosystem most people might see their role as shrinking?
Of course, everybody who has now a huge market share providing the whole chip will lose something. That's for sure. Because we create new competition here. And of course, each and every company who will lose something will fight. That's what I would expect. And that's okay.
Right, I guess another way of asking that same question is, I'm thinking that you might see the markets expand, cell chiplets beyond, and there's a balancing act. Have you worked any analysis that's looked at whether those people whose business models have been disrupted will ultimately be beneficiaries by adopting this?
We did some guesswork on what can happen, and we see even for the players who are at the moment doing the monolithic SoCs, the vendor closed SoCs, that there is a good chance also going into chiplets on their own, providing just a piece of it, but with the benefit that they don't need to do all the automotive specific things. And live with the 7+ years return of invest we're usually having, and having all these upfront invest, and maybe have more reuse from other industries. That can be a chance, but I'm not the other guy. I have no clue what they really think about it. We just did some guesswork.
My question is a two-part question. It's around functional safety. First thing is, how much additional complexity will a chiplet-based architecture add to your functional safety requirements and the certification process? And second is, do you see any new standards that need to be created for this space? Or is the current standards that exist sufficient? And especially around hardware software.
Okay, let's start first with the functional safety. I think we can make functional safety even easier with the right design. If we design it from the beginning, having functional safety in mind, especially for ADAS level 4 already, then we can make the hardware design in a manner that the software can be easier deployed, can be easier brought to an ACD, and we can hopefully encapsulate it in one time, not distribute it. If you make it wrongly, it can be hell, I would say. If you do it right from the beginning, and that's why we think we need everybody from the mobility industry who is really deep into it, involved, then you can make it much more easy. And no, I don't see much, at the moment, not out of my head, much need for new standards.
But I mean, isn't that how do you get it right? How do you make sure you get it right? Right? I mean, you need to have some standards to make sure everyone's following it, so that you get it right and not.
Yes, that's why, for example, AMIC has created an initiative for a core program called VCP, Automotive Chiplet Program, where they try to create a reference architecture so that we at least have a common set of requirements for everybody. That's the basic idea.
Just maybe following up on that question, do you see different chiplets meeting different ASIL requirements that are coming together in the UCI?
We don't think that each and every chiplet should meet the highest safety requirements. So AZD should be limited. We should not spread limit AZD over the chiplets. This is our opinion, that we should not do this. And of course, if you do this, it will limit reuse. And it will create overhead. And this is something we should avoid. If we want to have multiple suppliers of CPUs and GPUs, we should avoid any overhead as far as possible. So AZD and C should be limited to the automotive specific parts. AZD, we will see. Not sure yet, but I think there might be a need, especially the interface needs to be simplified.
I think the way that you showed your chiplet partitioning with the base automotive chiplet, I haven't seen that before. I think that was really interesting way to distribute the problem, right? Where I've had a different view on how I see chiplets, right? The more traditional view, where you've got the compute, your accelerator, all of that. But I think that where you centralize on the automotive base chiplet, which may have different safety requirements, and then everything else is an add-on. I think that's a really interesting way to put it.
Yeah, we have some different things in mind when we did this. One thing is also that we hope that these guys can be stable. even maybe over a generation. Therefore, the next generation, and they can be in older process technologies. They are serving automotive for longer, and then we can maybe also, and that's what we're also discussing about reliability requirements, everybody else involved. It's a thing we can discuss as we need to discuss.
How do you ensure differentiation if you push for standardization?
That's a tricky question because it's in line usually. What we think needs to be standardized is the order part. And so you need to say, okay, this is the draw space you're having. These are the interface requirements, but how you implement it, up to you. How efficient you do this, up to you. Of course, we need to say this is the ASIL level, but something a little bit needs to be specified. But we think collaboration is necessary on spec. Competition is always on implementation. So spec needs to be, but I agree with you, it's a real thin line. And of course, if you over specify, you will have no competition at all because everybody will back out. You cannot differentiate, and if you cannot differentiate, there will be no competition because nobody wants to do this business. Totally agree.
We're feeling how we want to deal with this grab rate in future for this kind of chiplets. If I have a vendor-specific SoC and it's malfunctioning, I just come for the stock vendor. If I have now an integration of many chiplets and one of the chiplets is not working, is the integrator paying for everything, or?
That's the business challenge we are facing. That's why we think it's necessary to create the integrator. Somebody needs to be product responsible. I highly doubt that anything else will be accepted by the automotive industry. There needs to be somebody who takes over the responsibility, and this needs to be priced in the end. So one partner. I highly doubt that any OEM will ask, oh, this is a CPU, this is this vendor in this room. I ask him, no. There will be one product responsible. Otherwise, it won't work.
So there's been a lot of success stories in open source software, like Linux and that. Do you have any successful areas or maybe areas that look promising for like an open source hardware area right now?
Out of my mind. Not really commercially successful.
Yeah, you see there's a lot of barriers maybe right now to that.
At the moment, from a chip perspective, nobody ever did this similar. Of course, you did multi-die packaging or multi-chip packaging, which are, yeah. But it's not the same. No, I haven't any. I think this is quite new. This is quite disruptive. How it should work, because it disrupts not only the technology, it disrupts also the value chain. And from my personal opinion, we talk really about disruption.
For the so I mean the chiplet ecosystem makes sense when you need a vast amount of compute, right? At what level for autonomy do we think where that transition happens, where a single SoC cannot keep up, and so chiplet would bring the price or cost reduction? Okay, if you just look into single domain, we say we can maybe think about, depending on the feature set you put in and depending on the OEM, because level 2 is not equal level 2. Ask 2 OEMs, you will get 2 different ideas. Yeah, but level 2 plus, maybe it's on the border. Everything above, it's okay. Fusion is good. Yeah, if you put IVI with on top, perfect. Then it will save costs. And IVI wise, you need to go into the higher segments. To me, it seems for the OEMs, right? That's gonna be the big attraction, right? And
Yeah, but you cannot address the mass market with the other two people at the moment. This is what work commercially works. Might be working from a TCO perspective for the commercial vehicle guys, but not for the youth players and passenger. And I highly doubt that any chip in the world can be successful if it's not price competitive. Nobody will pay extra for flexibility.
I think one practical example I can give from my own personal experience. We didn't call it chiplets at that time because we don't. So it was 2018 to 2020. That time we used the Xilinx off-the-shelf board, took it, and we developed our own gateway. And we had to develop our own vehicle gateway because the kind of architecture was totally new and the current available gateways were not able to handle it. And we could not do this kind of a DVC file approach. So we had to do an XML file approach of changing signals directly on the fly. And it worked amazing. Cost would not have been sustainable, but the whole concept of an OEM going in and quickly developing their own solution, that worked. Within 2 years. We were able to have gateways working with the whole vehicle. That's a practical way of just giving an example that it's highly possible. We didn't know what we can call it at that time, but we were able to do just with off-the-shelf Xilinx code.
Of course, now if you want to do this now and want to do the real industrialization, of course, we have to be price competitive from the beginning.
Yes.
Yeah, this will be one of the challenges. Yeah, not only flexible, but also price competitive.
Yeah.
But we think it's feasible.
Yes.
Post, not tomorrow, but maybe a sophisticated.
Because at that time we had no solution. So we had to do it. Yeah. So we took the hit on the bomb, but ultimately it worked. So it is highly possible if you can do it in scale.
Okay.
We have about 15 minutes left if anyone wants to have another conversation.
Oh.
Keep going.
One question. Software point of view. Does chiplet make software development easier or more complex?
We think it should make software development more easier. And we should start, that's what I mentioned, we should rethink the hardware for a future speed. Right from the beginning, thinking what kind of software rules do we have? How are they distributed? How we can ensure freedom of interference with hardware issues? How we can make sure that the organizational structures can be reused there at OEMs and tier ones there to implement the software. How we can distribute the functions much more easier, how we can standardize system behavior in terms of booting, in terms of reset, in terms of error handling, diagnostic. All these things, this should be considered from the beginning, and we need to collect, as the industry and collectively the requirements for that. To really design it. And that's why we think that this thing like an automotive base should be helping us. I think Bosch has did some experience with sensor with domain fusion, implementing IVI and ADAS on a single server with an hypervisor. And I think we are pretty aware of what it means from a software perspective at the moment with existing chips and what we can do better. But I assume a lot of other people in the industry are aware of this as well. Maybe of different problems already. So that's why we think it's important to have this together. Yes, if we are not making software development easier, we are facing a challenge as industry.
On that point, right? Is it so currently, if you look at the current monolithic chip architecture, right, the software is developed for just one combination of things that are put together. Now we'll have to somewhat make changes in the way software is done as well, right? We can't use the current model for software development, stack development. That is what I'm talking about, not the application level, but how does the firmware, the middle, those things, how do we bring those things?
Yes.
that requires a change in that level to make it easier at the higher level. Right?
Exactly. That's what I think, and that's why I mentioned at the beginning, we maybe should sit together and talk about the structure and the requirements about it.
It puts more effort on the middle levels to make it easier at the high.
It takes more effort, but we have to carefully design it that it does not need more resources. And that's always a constraint.
You mentioned functional safety.
I haven't heard of it, but yes, there will also be cybersecurity challenges, of course. Yeah. We need to think about new attack vectors with this chiplet approach. We may need to think about how to make it, how to be sure that chiplets coming from the right sources. Not that somebody put a fake chiplet in. Things like that, yes, there are some new attack vectors. I'm not sure how high the probability is that this can be done easily at the beginning, but later on, of course, it will be possible. And of course, you have interfaces, you have die-to-die, and if you have an interface, somebody will find a way how to penetrate it. Yes, I did not mention it, but it's a point.
Yeah, my name is Joern-Ole at Aura. We are a startup company developing radar. So, as you might know, radar is highly integrated single chip SoC currently. As the central processing and much compute becomes available, I believe that there may be different decoupled disaggregate architecture that can be applied to the sensors. So, could you offer some perspective on maybe how to take the radar technology with this new architecture?
Me personally, to be honest, I don't think that this new architecture will have an influence about how intelligent or not intelligent radar should be and can be. This is a task which will be not solved by chiplets. Of course, if you centralize everything, maybe there might be tendencies that one or the other company says, okay, then I will just pass raw data through. But I think this is more a task of the electrical engineering guys, defining the electrical architectures. It's nothing to do with chiplets in general. So I'm the wrong person to ask. I think other people in the room who are more experienced than me answering this question.
Are you talking about 4D digital radar or the traditional radar?
4D digital radar, yes.
Yeah, 4D digital radar, there is a big application for this.
Yeah.
Because of the sensor fusion as well as the processing on the edge. So the cost of reducing the 4D digital radar, the cost is pretty high. And the faster processing capability that is necessary to basically not use LiDAR in a car, therefore the radar has a big opportunity. So that's why this would be a good way.
I think where you also need to consider that which of the sensors are synchronized, that will not be. So on the chiplet side, we need to think of who have specific computing functionality demands need to bring into the chiplet system network. So is it just the DSP what we need to use, or do we need to have additional computational tasks? Because what this architecture, what would it present, basically reflecting, we are looking into individual parts of subsystems. What do we need for video processing, for radar processing? What do we need from respect to electronic appearance, etc.
The question about it's the future of this system and software-defined vehicles. So we are right now at an inflection point where people are talking about software-defined vehicle on one side, which calls for
actually standardization of, let's say, the computing hardware, like it happened 20, 30 years ago for the personal computers. Basically, at the end, you have one motherboard, a big chip that can do everything, and then you type the functionality just from software, but the chip can do everything, and it's kind of standardized, right? On the other side, you have we are calling for chiplet-based system because we are trying to we think from an automotive standpoint that hardware software co-design would save costs as well. So these are two solutions that, in my opinion, cannot coexist, can they? That would be my question.
From my perspective, this is exactly the evolution. When we look back a couple of years at the beginning of the chip industry, all these chips were highly application specific. Then we entered the age of generic chips for computation. That's what we see in the laptop, in the gaming station. And now we are coming back into the mixture, trying to use generic parts and put it together in an industrial specific way, and manner serving the industrial specific needs. So we will have specific parts and generic parts in one system. That's basically the idea. So this means it can coexist. For example, IVI should not be, or infotainment should not be with too many restrictions. Yeah, besides maybe some examinations, but we should use generic compute.
So just an example, I come back to the example of personal computing industry. For instance, IVI for me would be the GPU part, right? So is it something that and again, I'm not questioning the technological solution. I'm just questioning, is it something that can coexist? So let's say a motherboard-like solution with big chips, a GPU, for instance, for IVI on the side, and kind of a rack system in the car, or a chiplet-based solution where we promote flexibility, but also it comes with a cost for the software. So I'm just, in my mind, there are these two paths, and I'm trying to find out whether they can coexist or if one of them will survive only.
That's a good question. Actually, it's a good one. I like this. I like to have questions thinking about maybe later. I cannot answer this at the moment. I think it's a good one. Can this coexist? Can we have exchangeable, flexible hardware concept with huge generic chips like in a rack system and a chiplet-based approach in parallel? At the moment, I do not see a reason against it, but we really have to think about it. That's why I love to talk on conference, because there will be always a question which I cannot answer. And that's good. Actually, this is too new to answer all questions.
Tomorrow in my talk, I'll give you an example, show you pictures.
That's okay.
Joern, you made a comment about your company doing some work on the fusion side of things, and that you have a pretty good grip on combining IVI and ADAS software, for example. I think that's one thing that, and you even said it in your talk, starting with the software side of the world to define these chiplet-based devices. So sharing those experiences and how you went about keeping an effective partitioning between the two groups. My background when I was OEM and Tier 1, ADAS group and the IVI group, give them one piece of silicon, say, hey, chips, it's some things that can cause a little bit of tension. So from a semiconductor world now, understanding how you guys manage that might help in terms of the definition.
As soon as we have it complete and we decided to share, we will be the first ones.
So Elizabeth, you gotta get AVCC to be the clearing.
But we do have Austin Payatoli here, and maybe he would like to make some comments.
Yeah, I would say that is still in a early phase in general for the industry. You might see few SOCs supporting this single SOC fusion, and everyone is designing it differently. You might have multiple cores of CPU, GPU you can cluster together and divide it for few for ADAS, few for cockpit or whatever. But in the end of the day, if you divide it, you are missing your reallocation of compute whenever it's needed. But then at the same time, you might need to keep it separate so that there are safety elements and security elements applicable in one side. And then you have connectivity coming as an entry point for security. And you have to keep your ASIL Bs or Ds still safe and functioning and reliable and secure, right? So we need a dedicated partitioning between the domains at some point. But again, you cannot have two big GPUs. You can have, but again, the cost factor will come into play. You cannot have like 32 cores or whatever, right? Sometimes you might need to scale down. On the higher end solutions, I would say it is literally putting in two chips onto one would be the best solution instead of even the idea of having a rack system. I think completely that's also making sense. You need to scale up, you need to scale down. Thermally, it's a different scenario when you combine these two big processors, right? You have to take heat from this 30 millimeter by 30 millimeter, whatever, right? That number, it's going to be huge. We are talking about 600 TOPS, 700 TOPS, 800 TOPS, and you are talking about 1000 watts, right? It is not going to be easy. So keeping it separate is relevant to some scenarios, but at the same time, there are some like the memory bus. You share it partially. You might not have two pieces of UFS in the same. So you are reading from the storage in parallel. You are reading from DDR in parallel, right? Both the domains. You might be watching 4 movies on 4 screens, and you might have your ACC and even lane change happening in parallel. The same camera stream might be used for one function. Like for example, if you have a mirror camera in your side mirrors, but the same camera might be used for ADAS processing for lanes or whatever. Right? So this is where there is no right design. The right design is always having equal functioning parallelly happening, but then you are going to keep the size and the cost and scalability.
It's interesting that you differentiated between the very high. Because that's where, when we think about chiplets, I mean, how we like Mr. Low, Mr. Low IPI and Mr. Low ADAS, right, is the most cost sensitive. So building into your chiplets the flexibility that even the interface of UCIe costs silicon. So striking this balance between where is it remain a monolithic chip or a very dedicated set of chiplets so that we get them on process node versus all of the flexibility to do fusion and all of these things that you talked about. And how do we do the dynamic loading? Because we obviously can't interrupt the infotainment system that makes somebody else talk to their car. And now we suddenly need to run an LLM and at the same time, there's a very complex scene out there that we need to process from a perception standpoint. That's what we struggle with as a tier.
Yep.
Is making sure that we get the right thing. And I think it was already mentioned, these chiplets at the advanced process node are extremely expensive to develop. It's not only that, it's the opportunity cost. Putting resources on that chiplet, which is something.
In one of the statements he was mentioning about you don't design ASIL into every chiplet, right?
Right.
You can, but then it comes at a cost. Or you do put 2 ASIL chips simultaneously for maybe for the AI cores. If you want ASIL on the AI cores, you run it parallelly. You have 2, so simultaneously you are getting the video feed and doing all the processing in parallel and setting it out. But then you get the cost implication, you get the heat implication, and then finally you have the packaging, right? You are touching everything. But if you build that same amount of redundancy on a single chiplet, the same, you have the same problem. But that is where I think the idea of the base die taking care of most of this ASIL CBD stuff, and then you make sure the technology is enabling the confidence so that the decision can be happening that automotive die.
Brought up another topic, power.
Yeah.
We want to collapse everything. Oh, okay, what does that do to your thermal?
I don't, I never said it's easy. So how much time do we have left?
We are out of time.
Last question somewhere, or should we stop and use the coffee break and talk further?
Yeah, let's use the copy.
Okay, then thanks a lot for your attention.
All right, thank you, everyone. So when we started planning this conference back in Q1, the very first word that was put on the page was chiplets. And so I'm thrilled that we were able to kick off the conference with chiplets. And this conversation and the dialogue that's happening right now is one of the most important conversations that are happening in the industry. So I'm really happy that you're in the room. Please continue it while we're in the coffee break. Just a quick housekeeping note. So there's another conference going on the other side of this partition in the conference room A. So I would encourage you to only eat the food that's in conference room B, where we are. Because we might have taken a little bit from conference room A. We might replace it later. But I didn't mention that earlier, and that was my bad. So there's also the fruits and pastries and things over here and drinks over here. And also, when we come back from the break, I encourage you to get your coffee now because we've heard how loud that coffee maker is. And it's great coffee. We grind the beans here, but it is a little bit loud. So we'll try to get it all in before the next speaker. So we'll see you back here at 10:30. And for our guests online, we will see you back at 10:30. Thank you.
He's still with us.
Yeah.
Getting everybody all settled in here.
Sir, anywhere, any chance to? No, I think I have the same idea only. That's what I was saying. I can check with the team. I did not organize that, so it's a sales team. I will check with them. Yeah, I'm meeting the manager.
Okay, welcome back from break. Thank you all for your patience as we figured out catering and drinks, and there's a lot of people in this room. I wish the people online could see the audience that we have here. So next up, we have a great addition to the panel, to the speakers today. So Partha Goswami joins us from PG Mobility. And Partha brings an incredible perspective, and actually one of our colleagues had seen a presentation earlier this year and said, we have to have him join us here in Farmington Hills. And we're so lucky that he's local. So Partha will take the stage and talk about looking backwards at where autonomous mobility has been and where we're going in the future. So please help me welcome Partha to the stage. And I just have to figure out his slides because they're a little bit different than everyone else's.
Just press the, right?
Yep, just press any of the keys. Thank you.
All right. Thank you, sir. And thanks for the kind introduction. I think I have to live up to it now. So good morning, everybody. My name is Partha Goswami. I'm the outlier here because you guys are the technologists and I'm the observer. Okay. In fact, that's been my job literally when I was at GM over the last decade. And I took the retirement last year and I've been independent freelance since then. But basically, I'm still doing the same thing because one good thing is industry is changing faster than ever. So those of us who follow the trends actually has a more than a full-time job at hand. If I'm on vacation and kind of disconnected for a week, I feel like I'm back to the Middle Ages. But things have changed, right? So that's the background. So Elizabeth and I were in an event earlier in the year, and which was about software-defined vehicle, something I've been looking at for a number of years now. I'm not the expert, but again, there's so much rich material that's going on in that particular area. So the thing was, can come back and talk some of those, and of course, this is AVCC. So I have to put it sort of in the context of autonomous, which is another area I've been looking at also for a number of years as part of my trend observation. I've been advising our GMs, ADAS leaders, as well as policymakers on the subject. So I kind of bring some of those together and talk about it. So this is what I'm going to talk about, and I have about half an hour, right? Sarah is not here, but I'm going to So I'll talk about what SDV is basically, a little bit of background, and also what does it mean from a vehicle architecture standpoint. Benefit, but most importantly, challenges, because that's really the big deal. The challenges and how it's actually slowing down the entire adoption of SDV software-defined vehicle. And then I'll bring in and add a little bit more perspective on autonomous, and then we'll have a summary. So as an introduction, back in the early 2000s, the car was a one-off device, meaning we put it together, industry puts it together, and we goes to the dealer, whatever the sales channel, we sell it and we wash our hands off it, we are done. The guys who built it, they move on to another new car program, okay? And that's it. So the best day of that car is day one. Okay, and after that, everything slowly decays, both in terms of value as well as features. They become stale. So in the middle part of the first decade, around 2006 time frame, when smartphone came about, consumers were exposed to the idea that, hey, here's a device which has a primary purpose, which is to make calls, or had a primary purpose, I should say, is to make calls. But then it's used for everything else, really. So it's a platform for many other functions that we use in our daily life. So this idea of, can the car be something like that? Can it be a smartphone on wheels? Now, I will remind you that that particular, let's say metaphor or whatever you call it, the smartphone on wheels for car is highly inappropriate, because smartphone is not a safety critical device. Okay, car is, if your iPhone or Android crashes, it's an annoyance. If your something happens to your vehicle, that's a life and death situation, right? Having said that, the idea of a platform though is very powerful, and that literally started changing a lot of thinking in the car industry, right? So around middle of the next decade, actually, soon after Tesla came into being, or first Model S came into being, this idea of case became very popular because all these technologies started coming to the cars. Connectivity, of course, telematics was there for a number of years before that, but connectivity started being more mainstream. Autonomous, of course, ADAS, autonomous, software and services, the idea of software and services, and then finally electrification. Okay, together it's called a case. So a lot of those requirements started coming in, but the car basically became inherently the same old brick and mortar architecture, right? So there was a need to change that. And what industry saw, that there were car companies, the NEVs, new energy vehicles, or the new electric car companies, many of them from China, but of course, the most prominent of that being Tesla. Okay, they started with a clean sheet architecture. Okay, that's the idea of this service-oriented architecture came into being. So that really basically created the idea in consumers' mind, and certainly in industry's mind as well, the idea of vehicle as a platform. Now, from the from the OEM side, they started dreaming the idea of more control and flexibility. Hey, Tesla adds functions, features overnight through over-the-air update. They design their own chips. They control the entire value chain. Let's do that. Easier said than done, but that was the inspiration or motivation. On the consumer side, the idea of frequent refresh, my car remains new. The day one is no longer the best day. It keeps getting better, or potentially it could get better, right? So those really created the idea of software-defined vehicle. Okay? So the question is, what is SDV? What is software-defined vehicle, right? And you might say that that question is put to rest, but actually it's not. So the true answer is, what is SDV? True answer is, depends on who you ask, right? And usually they can actually vary. And the reason the answer varies is because experts look at the topic through their own lens, right? So what I did is I looked at a few companies who are in the business. QNX, BlackBerry QNX, Sonata is a software company, Eclipse SDV consortium that many of you know, or maybe even part of. And I looked at how they are defined it. So I simply went to their websites and I copied it here. And I don't want you to kind of read through that, but I highlighted a few words which kind of bubbled up in my mind. And I think they I think, are the attributes. So the thing is, rather than trying to define, I would rather like to discuss the attributes of what SDV is, right? And without getting stuck into this, minutiae of the definition. So for me, there are two key areas that are important. One is, again, on the consumer side, which is what I already discussed. But this chart kind of shows that. So if the black line, the dashed line, if you consider as a kind of a one life cycle of a vehicle, okay? So within that life cycle, just like our smartphone, consumers would like to see maybe new features are added. And within those new features being added, like to see updates, okay? In 2014, I got one of my earlier SDV calls from my leadership. Hey, can you look at what Tesla is doing? The consumers seem to be very excited because they wake up in the morning and they see in their dash saying that your suspension setting has changed overnight. And everybody's so excited. I got a new suspension setting, right? So it's kind of that same idea. And everybody wanted to replicate that. Now, that of course requires a lot of changes, how vehicles are designed. And one of them is this idea of decoupling software from hardware. Essentially, and that's kind of my cartoon of what SDV is, which is you have your underlying hardware, and then every function in the car is an application. And essentially, there is a middleware which connects your hardware to software. That's kind of at simplest level, is one way to define SDV. You may have other definitions. So why SDV became so popular, or why everybody's talking about it, right? And the main thing is, if you look at the right side of the page, that's the current architecture, distributed architecture. We need a new function, be it ACC, be it sideline zone, the way, at least for the last decade, the car industry has done, add one more ECU to it. Okay, I need another additional function. I need whatever that function be. I add another ECU. So we have grown over time into a collection of fragmented, distributed ECUs. Right? Suddenly, that's not scalable. At some point in time, we say, there is no more room. Currently, an average car probably has 50 plus ECUs, right? So that's really, it cannot expand. It's not suitable for high, intense, complex computation, and suddenly doesn't have any fast, high-speed data sharing mechanism. So that's the idea where decoupling the software and hardware comes into play. Centralized idea of a centralized computing rather than individual small ECUs. And then finally, high-speed Ethernet connection. So out goes the old architecture and comes a new one, right? And I just borrowed it from NXP, their latest, the way they draw it. And again, I had an older one. They said, no, use this. This is our latest communication PR approved version. But the key idea is simple. You again have a central compute platform. Maybe you are separating the various functions. If you can read the central box, you have IVI, infotainment, you have ADAS, autonomous functions, etc. Then you have other zonal gateways, ultimately to connect to the specific functions in the vehicle, right? So that's the general idea. Good so far? Okay, and then, but here comes the rub, right? It's easier said than done. The transition from one to the other, from our distributed architecture to this ideal, clean, decoupled with the system with the central architecture, central compute platform, it sounds pretty good, but it's pretty hard and painful, at least for a large OEM. Now, I think there was some discussion in the previous presentation, the idea of the role of tier ones and things like that. One thing that comes to my mind, and I have worked in different car companies for 30 years, and I think the way they move is like a large ship, like a aircraft carrier, let's say, and it takes a long time for the aircraft carrier to turn. Right? So why I'm saying that, that's what I'm trying to say here. that transitioning from the left side, with the fragmented distributed architecture going all the way to a relatively ideal centralized system is going to be a long and hard one, right? And there might be some intermediate steps, like the one in the middle with domain controllers and whatever the design be. There might be various different flavors of that many of them maybe you guys are in the middle of designing right now, right? And that can be a very long uphill path. So the other thing I wanted to say was, if you consider a tier 1 or a tier 2, smaller battleships, one thing you have is you can change direction a little faster than the OEMs. So while OEMs are trying to struggle and change direction, I think you have a little bit time on your hand to change, but you guys also have to change. Right? I think that's the message. There is no other way to do it. So one of the changes or the pain from an OEM standpoint is this idea of continuous product development, right? So right now, product development process for a car is very linear, meaning and fixed, meaning, GM used to have this very well laid out VDP or vehicle development program or something like that. And the idea was you start from day one, and then you have very fixed milestones, and out comes the car at the other end. When the car goes out, everybody forgets about that. The guys are dismantled, and then they go to other programs, right? Now, of course, when you are saying that, my car, the best day of my car is not the day one, but it's going to be further down the road, you can't just wash your hands off it. So you have to bring this whole idea of software, centric product development where it's never done, right? If you when I talk to software guys, one thing they say, hey, you have to keep in mind, software is never done. It kind of goes on. It's like a continuous process. So, and the OEMs in particular don't have internal structure to that. So they have to move from their traditional linear process, the V model that you are familiar with, to something like continuous loop. And I'm sure all of you are more familiar than me. This idea of continuous DevOps loop, going to shift left, idea of shift left and shift right, where basically you start looking at things, much earlier in the process. This idea of continuous integration, development, and testing. So that's the part OEMs are struggling to change. They are making organizational changes. They're experimenting with organizational changes. How can my organization be designed? Right? I mean, GM created a group called Software and Services, and I'm sure all car companies, have been doing something like that. All of us know the story of VW, and there's kind of roadblocks they're faced with their current state. The Volvo's EX90 development, if you have studied CIM lately, there are several articles that were published in terms of their struggles. How EX90, when it came about, it missed so many things. It came without some basic features. The compute platform based on NVIDIA, the reboot time became much longer than it should be. A lot of misses, right? And again, it's just a reflection of the struggle internal to switch from the old paradigm to the new paradigm. The other thing is, at least my experience based on the 2 car companies I have worked in, it's very siloed. The product development structure is very much siloed. The whole car company is designed by chassis, by body, by interior, and things like that. Everybody does their thing, and then they put everything back together at the end, right? But now that's not going to fly because every function is interdependent on something else. Take a very simple function, it depends on data for some other subsystem that I need to, get to the internal network. So this idea of function-based vehicle development is something new. Okay, this is a chart I borrowed from Aurora Labs, a software company. Some of you probably know, and Mark Richards, he left the company now, but he sent me this thing, and when we were discussing these topics, this idea of cross-functional product development, and not just cross-functional, also interdependent, right? So here's a very simple example, which kind of shows the idea very eloquently, which is turn signal. Just a turn signal, very simple operation, right? And if I have to make a change, let's say if I'm doing a software update, I have to keep in mind that it is dependent on so many other things. The specific software may be tied to, say, your ACC or even regular cruise control and lane departure warning and things, all these icons that have to light up in your HMI. So it's tied to the cluster display. It may be tied to the head-up display if there's a head-up display in the car. And that sort of stuff, right? So a simple function like turn signal may be connected to 5 other different functions. And so when I'm developing the software, I have to make sure how they're interrelated to each other, right? And then I think of a more complicated ADAS system, or maybe a level 2 or level 3 or whatever, right? That becomes, it kind of, the complexity grows exponentially, right? So, and the other thing is, one of the things that it might be very nice to say that, oh, you know what, I wake up and through OTA, I have a new function. But then it also means that there may be some new vulnerabilities. Somebody, sent an update out, but then it touched on some other things which might have been missed. And then there were recent examples, if you remember, without naming the specific OEM, they released pretty broad range of updates to their infotainment systems, okay, which is really good. Then, but for maybe 10-15% of their vehicles are bricked, the infotainment systems are bricked, everything was dark, right? And they had to come back and fix it. So basically something slipped through, some of the updates did not take care of some of the things, all right? Now that also reminds me of the CrowdStrike event that happened not too long ago. And it was nothing malicious about it. There was the software just slipped through, somebody didn't check, but it was blasted through the entire ecosystem of about 8.5 million devices. But the effects were striking. Airlines to grocery stores to banks to coffee shops, whoever was using the CrowdStrike system, they basically were stalled for several days, in some cases several weeks, right? So those are the things we need to keep in mind when you have a very cross-functional and interdependent software development integrated into your vehicle. So one of the impacts on AV solutions, ADAS solutions, right? We're trying to just move from this distributed system to whatever the system is on the right-hand side. Let's say ideally very centralized architecture, very ideal software-defined vehicle. But you had a lot of work that has to happen before I can shift. GM, for example, has level 2 hands-free system, Super Cruise. Ford has Blue Cruise. I think Nissan has Pro Pilot, and on and on and on. And many of them are developed actually in the older framework, the one on the left-hand side, right? And now they have to move everything to the right-hand side. That's a lot of work. Suppliers have to be involved. The OEMs have to, roll up their sleeves, and maybe they write their own software. So they need to understand what software works, how and where. That's a lot of work. Okay. I'm not being pessimistic. I'm just trying to highlight some of the issues here. Okay, value chain transition, and we talked about it in the previous presentation, right? So this historic hierarchical system, right? OEM at the top of the food chain, then you have tier 1, 2, 3, 4, whatever. That doesn't work anymore in this particular system, right? So from this traditional pyramid structure, what we are seeing right in front of our eyes is a transition to a more something like a network, okay, where OEM and the tier 1, they still have a prominent position in that particular network, but then there are a lot of new players that you have to work with, okay? They bring a lot of new expertise. Someone said, hey, the tier 2 has a stronger hand in that particular technology, okay? And that exactly is the case. So this network shows tier 1 with the tier 1 to whatever. Then you have startups, okay? And then on top of that, you have these big technology companies like Qualcomm, NVIDIA, Intel, whoever, and Google, right? And in many cases, they are engaging with the car industry in many, many big ways. If you look at Qualcomm's, if you look at their quarterly reports, you'll see that every time they highlight another new win from another car company, and they are in many cases they're acting like tier ones, right? So industry and the entire traditional value chain has to contend with all that. So that means actually it means many different things. I just highlighted a few. If I start from the bottom, the way I wrote it up. First of all, this technology industry, again, the big techs, as well as the small, tiny startups, they are engaging more directly with the OEMs now. Okay. And of course, what does it mean for tier one like Bosch, right? We can come back to that discussion later. I had conversation with the corp strategy teams in some of the tier ones, your peers, and I think there are many things to discuss here. Other thing is OEMs have to learn to be less transactional and more partnership oriented. Company like GM, they would write specs and hand it out to you, Bosch, go ahead, run with it. And then, we'll just dictate and review and we'll see where things go. Right now, you can't do that anymore. You have to have a lot more partnership, because if you want to take control, which you want to be like Tesla, then you have to decide that, hey, I also take some roles, I have a responsibility now. Hey, maybe I have to do some integration on my own now. Yeah, I can't just hand over a spec to the tier ones, right? So that requires a whole set of new discipline, new talent, and new organizational structure. So, and the impact will be, if you look at the top bullet, the impact actually is on leadership, on people, on culture, everything. On top of that, there are new things happening, right? Which kind of now also becoming part of the value chain, which is more recent. So if you have anybody hasn't heard about SDVerse, which was a marketplace which was established in early spring, actually September 30th, a week back was their first day. Idea is create a marketplace for software, hopefully certified in some sense. But the idea is that all the participants can go in and take the softwares. They don't have to create everything on their own. That's the idea. So this business to business marketplace is another concept which is coming to the automotive value chain related to the software defined vehicle design. And that has many, many significances. I don't know, maybe Bosch is part of that. It started with GM, Magna, Wipro, and a few other guys, and I know the membership roster has increased. But again, you can be both buyer and seller in that particular marketplace. So the point of everything is that this whole transition to SDV is not a fixed point A to point B journey. It's really a journey to a particular destination, which can come in many different shapes. So if you look at this particular chart, right, and the axis shows how OEMs are trying to be more vertically integrated, in theory taking more control from the supply chain, and the right hand side is the accountability part. They have to develop a lot more expertise in both software and hardware. So the top right section, the box is really the goal. Where I'm designing my own software stack, I'm designing my own chip, I'm managing the cloud and all that stuff. But then reality is the OEMs are probably somewhere in between. They're trying to build their competence in both hardware and software. They are falling back on common standards. Okay, and that's a big deal. This car industry traditionally has been very proprietary. I want to do everything my way. I want to do everything BMW way. I want to do everything GM way, whatever, right? Can't do that in SDV anymore because you just simply don't have the bandwidth to do everything you need. And adopting open source, okay, that is also something new. So the whole Eclipse SDV is based on that particular premise. So the thing is, OEMs want to get more control and flexibility in their development, and they have to have a lot more dependence on organization like Covisa, which is based on data standards. Sophie, many of you are from ARM. you know about SOFI very well. It keeps SDV, orders are, etc. But there are many other TBD, TBDs and open issues. Okay, one of the thing is long-term maintenance. What happens? We are talking about today or maybe tomorrow. What happens the day after? What happens the year after? What happens the decade after? Okay, what would happen to your software that you introduced in the vehicle in 2024? What happens to that in 2034? So this idea of maintaining compatibility software between generations of vehicles is something the car industry has not only hasn't done, they probably are not even thinking as much about. There are so much things to do right now. Traceability, we are very good at providing traceability for physical parts going back to 10, 15 years. What about traceability of your software? What happens today? You work with AWS, tomorrow you're working with Google, your cloud system changes. Does your entire tool chain work? That sort of stuff, right? So anybody know about a company called WM in China? It's Weltmeister. Okay, it's a company that has been around for a while, and they actually have about 100,000 cars that they sold over the last 5-6 years. Okay, the company recently went bankrupt. Okay, so one fine morning, the consumers woke up and nothing works because the support service, they're gone. You can't access the car because your phone app doesn't work. Or even if someone managed to get in, infotainment system doesn't, nothing works, right? And there's nobody, right? So what happens with an SDV? Either the car company or any of the suppliers, they go bankrupt. What's going to happen to that car? Okay. Those are the things I think are very open. So the bottom line is, car industry doesn't feel that we are all really ready to embrace and get going, full speed with SDV. It's going to happen in very incremental steps. A survey done by Alex Partners, which they published early in January, basically said only about 2/3 of the survey respondents basically say they are maybe moderately ready for this transition. Okay, and then most of the OEMs said they are not ready for open source software. 51%, the OEMs still favor proprietary software, right? And the number was opposite when the OEM versus the rest of the supply chain, when you talked about a mixed system where open source combined with some proprietary, so the ratio changed. So bottom line is there is a lot of long ways to go to even embrace the entire open source culture in the car industry. And finally, it's like the movie, right? Everything everywhere happening at the same time. So at the same time, we are building software-defined vehicle, a lot of investment, and I just mentioned some of them, a lot of open challenges. The car industry also trying to transition to electrification at the same time. Both are very, very high investment reach subject, okay, and we have never done. And then on top of that, we have to change the underlying architecture, right? And underlying the culture of bringing software into car industry, right? So those are big deal. Each of them are big deals, and they are all happening in the same time. And that makes things a little bit more complicated. All right, so let me switch gears, come back to AVCC and talk a little bit about autonomous technology. I have some perspective. I'll just bring a few things. I'll make some few comments, and I'll just throw it, and I'll see your reactions. So first thing is, when you deal with complex technology like autonomous technology, usually it takes a long time. But in between, industry has to put up with this hype cycle. Gartner hype cycle. I think many of you are familiar with. Maybe the idea is a new idea gets triggered. Everybody talks about it, especially now with the bloggers and the media and everybody, giving their opinions. It becomes very hyped up, and talking about robotaxi, right? I mean, you guys remember that by 2020 we are supposed to have 1 million robotaxis, okay? Right? Well, day after tomorrow we'll see what happens, right? So that kind of thing, right? And then when the technology is more complex, actually you don't necessarily have one hype cycle. There could be multiple hype cycles because everybody expects things to happen, don't happen. So in case of artificial intelligence, very good case in point. AI has been around, the core ideas have been around for decades, going back to 60s. And then things almost, robots are supposed to take over, but they didn't quite, and they kind of goes up and down in cycles. And experts, people call them the winter, the spring and winter of AI. So we have had several winters of AI since 60s, and we'll see what happens now with LLMs and everything, deepfakes going on. So I'm kind of trying to bring the same idea to autonomous technology, and I see the same thing. That, again, since the DARPA technology, the DARPA race, if you remember, going back to the early part of the century, when the idea came about, the groups are formed in Google, we've seen that Google Firefly, the pod, you remember the little pod without steering wheels, came about in 2014, and then everybody says 2 more years, you call and the car will come and pick you up. And it was not, again, I'm not criticizing the hype. I think that's how it happens. Everybody gets excited, but it's a complex technology. It takes a lot of time. So, when a lot of things happen, GM acquired Cruise, Ford acquired, or at least invested in Argo AI. And then in 18, Uber, who thought they would be the Uber of the autonomous taxi, they went and recruited, I should say, about entire robotics lab in CMU, right? And they said, we're going to develop in the next 2 years, we'll have all our taxis converted to autonomous. And then an accident happened in Phoenix, and they turned the clock backwards, and everybody kind of went back to the drawing board saying, hey, we need to be a lot more careful in terms of our testing on the road. And of course, at the same time, Argo AI shut down because they realized that they can really, they don't have a business case and they can't really sustain their workforce without any additional investment. So on and on, and over the Cruise robotics event last year, that kind of had its own effect, right? And we're kind of at a point right now where it's trying to go back. I have what, time up?
Yeah, your time.
Okay. But in any case, I think you get the idea. What I'm going to do is I'm going to skip my level 3 comment, which we can discuss later on. I have a lot of concern about level 3. A lot of car companies launching their level 3 functions. But what I would say is the robotaxi, coming back to the robotaxi, I think this is how things are going to happen. Today, we have fully autonomous trucks by Caterpillar and other companies working in mines. The reason they are fully autonomous and they are commercially deployed is because the ODD, right? There is nobody there. In the mines, nobody works. And so when you talk about on the right-hand side, the urban robotaxis, okay, that is probably the most complicated ODD, right? Operational design domain with maximum uncertainty, most dynamic, very unpredictable, and you have to share the road with lots of vulnerable road users, right? Cyclists, scooters, pedestrians, cabs, dogs, whoever, right? So I think in the middle two, the last middle mile cargo, and even highway hub to hub, if there are certain regulations are put in place, if there are more designated lanes, maybe those will happen soon. Okay, I don't know, but bottom line is more complex the ODD, further will be the adoption in time, and the robotaxi comes in that one. So that's really the talk, and the key takeaways are simple. SDV is the paradigm shift in automotive product development. There are lots of issues. So the aircraft carriers or the OEMs will take a long time to turn around. And meanwhile, some things we need to remember that we need to transition to a continuous product development process, which the car industry hasn't really figured out how to do quite yet. And of course, the vertical integration, the entire value chain shift that I talked about, that from a pyramid to a network, the very slow and uphill journey for the legacy OEMs to transition, especially when you talk about the complex functions like ADAS and other autonomous functions where you have to move them to a more completely different architecture. And again, ODD and business models probably will drive the adoption of the right AV application going forward. Okay, thank you.
All right, I could have listened to another half hour of that. That's fascinating journey. And thank you so much for that contribution. Partha will be around. If anyone has additional questions, I apologize. We are going to move on to the next speaker because we're a little short on time. And if you're online, I am seeing your questions in the Q&A. I didn't pay as close attention as in the keynote as I should have. So I appreciate your patience there. Our next speaker is Rajive Joshi. He's here as a dual representative. He is the chair of our software portability working group, and he also is here in his capacity at RTI. And Rajive is amazing. I'm going to get his presentation up when I give him the microphone here. He's published a wonderful blog series on the AVCC website, as well as he just did a webinar, which we can get you a recording copy of. And I am very happy to introduce Rajive.
Thank you, Sarah. Thank you. Bart's talk is a perfect setup for what I'm going to speak about. But before I get into that, and while she's bringing the slides, I wanted to just share kind of what happened last night. So arrived in Detroit, late night, go to the rental car company to pick up my car. And it wasn't the car I requested. Actually, it was much bigger. I said, well, it's Detroit. Things got to be bigger and better here. So it's the Motor City. So anyway, I picked up the car, figured out how to connect my phone, and then, I had everything working perfectly, right? Now my phone didn't know anything about this car. This car is a Jeep Wrangler, off-road vehicle. I've never really driven this before. It's nice, I have to say. But I'm like, how do I get here, right? So CarPlay, right? And what's beautiful about that is that these two companies had a common interface, right? And then as long as, my phone continues to evolve, never driven a Jeep Wrangler, but these work perfectly, right? So that's the power of hardware and software and software defined. And that's really what I wanted to talk about, and how do you connect sort of solving this problem of, the challenges that Parth actually so nicely highlighted in his talk. So I'm going to spend some time, maybe 45 minutes or so, I think is what I have, about building zonal data-oriented software architectures. And by now, if you had never heard of that term, you fully know exactly what that is. Of course, I'm pretty sure in the Motor City, everybody knows all of this stuff and way more. So, by the way, I come from Silicon Valley. I work for a small or medium-sized, I don't know how to categorize it, but some will say startup, but it's Silicon Valley, and tech sort of out there, and that partnership diagram that Partha had, we supply directly to OEMs, we supply to tier ones as well. So we are kind of in that sort of evolution of how the supply chains are evolving. That's where we live, and so. And I'm a system architect, so I work quite a bit with OEMs directly as well in my day job outside the AVCC. All right, so let's see. How do I move this? Is there a clicker or
arrows at the bottom right?
Arrows. Okay, I got it. Yeah, it's just I'm a Mac user. And the mouse is a little bit different. Okay, so human interfaces and computer interfaces still need some work. All right, we're going to talk about automation and autonomous interfaces. So this is kind of what I set up for the agenda. I don't think I'll spend too much more time on the first topic, but highlight a few points about the emergence of EE architectures, and then SDVs. Talk a little bit about some of the work we've been doing in AVCC with my AVCC hat on, and some of the work we have published in solving some of the challenges. And if you haven't seen our work, definitely check it out after this. And then dive a little bit into the data-oriented architecture concept, which really, if you remember Bart's slide, and he talked about how a turn signal affects so many different pieces and how do you solve that problem. I'll explain one way that industry has evolved to solve that problem. and how this approach of data-oriented architecture essentially gets you from, this reliable cabling, which is expensive, heavy, and what people are trying to get away from, to this nice, smart software wiring that allows you to evolve and have a very fluid architecture that you can update over time, and then talk about kind of the drive ahead in terms of how we move forward. So let's see. All right. So yeah, I mean, this is really a journey about the evolution of the cabling, really, from on the right here. Let's see. What should I use? You've got this flat architecture. I borrowed this slide from again from, in this case, Cadence slide deck, but a lot of the hardware companies have put out these kind of decks, so we don't have to worry about that. And then, today we see a lot of this domain-based architecture. We've got ADAS and IVI and body and chassis and other things. And then where we are going towards the zonal approach that you also saw. And really, the logical domain approach has allowed people to sort of work together, but still in their own specialty. And you still have a lot of cabling. If you open up a car and start to look inside and look at all the cables that go around, different colors and everything, it's a lot of stuff, right? It's heavy, it's complicated, and then if something breaks, how do you troubleshoot that? And it's not cheap, right? So now think about being able to take that heavy cabling and replace it with maybe just one or two cables, right? And all of that sort of different colored cables are just different data flows in this logical, software data flows, essentially. And you've got just really one or two hardware cables to manage. It's a lot cheaper from a hardware perspective. It's a lot more sort of flexible. And if you need to change things, you can change that in software. So that's kind of also another way of thinking about zonal architectures that I'm going to talk about. And now, in the different zones, of course, you have different functions, and you can match the form to function more appropriately in the software side. So let's see. Right. So zonal E architecture is really the market essentially evolving to reduce the number of physical components and cabling. And that's really what we are trying to do. We are trying to centralize and consolidate. And that centralization consolidation happening not only in hardware in terms of compute, which of course, and we heard on chiplets from, early in the morning from the keynote speaker, and then, but it's also happening in the cabling, right? In the wiring, in the communication, which we don't often think about because we kind of take it for granted, but that's sort of a complicated part of building a vehicle, right? So this is a big evolution that's happening, and so that's the centralization on the compute side, and then as that is happening, and you're trying to reduce the cables, what happens with? I mean, you cannot take the complexity out completely. Right? It's like a bubble. You push from one end, it pops out from somewhere else. Right, so you have to shift that complexity into software, right? So the software has to become smarter and more sophisticated. Like you have the compute to do that, and then you have also the communication technologies that those can handle that. So this is really sort of another way of thinking about what's happening in the evolution of the E architectures, right? So the software system architecture becomes extremely critical and important for vehicle development. And this is really why, this transition, struggle, chaos is happening in our industry today, right? And we are witnessing that firsthand, all of us, right? So really the emergence of SDV is about reducing cost and time in terms of building, and of course, lowering, consolidating the hardware, but also about improving agility, right? And again, Partha did a beautiful job covering these topics. I'm gonna show a little bit of a different angle to this. So automotive market trends, right? This is a slide I took from Gartner, and really the things to highlight is that the second largest market share by 2030, according to Gartner, will be software development. And this includes all aspects, of course, of software. And so I kind of highlighted that piece here. As you can see, this is the software portion. If we zoom into that more, then this is sort of a nice clip of 9.4% cumulative annual growth rate in the industry, right? So it's expected to be 83 billion. So this is kind of an estimate, and this is kind of the problem of how do you build a software system effectively in a way that's agile, that's flexible, that's cost effective, supports sort of the modern methods of DevOps and continuous updates. And so this is a problem we started to tackle in our AVCC work in the software portability working group, and this is how our technical report 005 came about. And so that goes into a lot of detail. I think it's about 70 pages or something like that. I forget exactly, but it's a fairly in-depth analysis. And so this is available, of course, as a free download, like all our documents in the AVCC. So anybody, please check out. Our documents are interrelated, so it's all. Oops, so them to move there, but did I break my presentation? Okay, so that's. Hold on, I have to minimize this now. This one. Yeah. So, just to simplify kind of the problem at a high level, and this is kind of the signal term problem that Bart talked about. Right? When you are building a software system, and now we're coming at it from the angle of building software rather than hardware, but we're talking about software for systems that are critical in terms of timing, safety, security, all of those aspects, performance, of course, right? And you think about a software system that needs to evolve, and let's say that this is the system design you came up with, right? The yellow boxes here represent software components or functions you can think of that do some things in software. And I'm not really saying anything about the hardware, so just think functionally. And those blue arrows represent sort of the data flows or communication between those software components, right? And let's say that this is the type of sort of communication topology you have at this moment, and you want to now add a new software component, right? What can that do to your system, right? So, well, you can see that the red arrows are the new ones, and they can impact existing software functionality in a very fundamental way, right? You might have to update, revalidate, test, verify, all of that, many other existing software functions. So it's a very intrusive change, right? And as you want to add new software functions, this starts to become, a complex problem, and especially it's order n squared, so it's a parabolic increase essentially. And so it starts to get complicated, and that is because you have tight coupling between the software components, right? And because of that, this system is hard to evolve. It also becomes really hard to use an existing software component. And now if you start thinking about the 20, 30-year timelines, whatever you start to think about, then this is even more sort of challenging, right? How do you sort of manage the evolution of the software? Right, so now at AVCC, our, the vision we have is this ecosystem of modular software components that can be composed together. And we saw a similar slide in the morning on the chipless from a chipless perspective. But it's really the same idea, right? You want to be able to take software components from different places and being able to connect them together. And just like the CarPlay interface, things work seamlessly, even though they were defined by different parties, they were built independently, perhaps at different times. But because they adhere to a common standard, a common spec, they are interoperable, right? So that's the idea of these communication interfaces that you need to sort of standardize on to have the software ecosystem. And what that boils down to is some common data exchange semantics in the system. So this is where the AVCC guidance comes into play, and this is this technical report, the TR005, is called the Data-Oriented Architecture, Communication Architecture for Automated and Assisted Driving Systems. And we are looking at kind of the problem interoperability and portability. So this is a little bit of a cartoon showing a compute platform, right? So again, conceptually, you've got some physical connectivity at the bottom. You've got some compute nodes. You can put whatever mapping you have, but you recognize kind of this pattern that you might have, software components running on different compute platforms that are connected, and some compute platform will allow you to have software components perhaps at different levels of criticality, right? So really the piece we are focusing on is the yellow part, the software components where the functions are. And there are two kind of arrows you see, the gray arrows, which really is I mark that as portability or system software. That's about how do you make sure a software component is portable, or you're able to take this piece of software and go from one compute platform to another, right? So that's the problem of portability. The other problem you have to solve is the orange arrows, and we call that interoperability, and that's about the software system, and that's about the ability of two or more software components, regardless of the compute platform, so that to work together out of the box, just like the CarPlay interface, right? Because they are semantically compatible interface. Right? So that's the idea. So we are looking at the problem of interoperability in TR005 in that technical report, and really then focusing on the data architecture, which we define as really the connectivity framework, the full connectivity stack, and the data models that describe the structure and behavior of the data flows that's captured by the data model, right? So that is what we call the data architecture. And we look at that, and essentially we have come up with a number of recommendations for the industry. So the first one, and again, you'll find all the analysis and the arguments there, so I'll summarize these here. The thinking is based on the idea that it's an ecosystem of components that work together by adhering to a common set of principles, right, of software system design. And these are coming from best practices. So number one, the industry should recognize data-oriented architecture as a way of building interoperable software components. And AVCC is adopting a data-oriented software architecture approach. Right, so that's number one. And then looking at standards, because you need, if you want to standardize, you need standards that allow you to support this kind of interfaces. AVCC is adopting DDS, which is an open standard from the Object Management Group, as its data-oriented communication architecture standard. And number three, AVCC is developing a baseline data model that's comprised of common data types that define the structure of the data flows that are, again, using the conceptual reference architecture. That's another AVCC technical report as a starting point. And then also common quality of service profiles that define the data flow behaviors. Again, there are basic profiles, about 7 or 8, that are defined in the AVCC technical report 001, such as streams, events, status, state, data, configuration data, requests, objectives, and so on. So those are typically high-level sort of conceptual type of data flow patterns you will see when you start looking at system software architectures. So that's TR001. And really then what that allows us to do is build a common data architecture for an interoperable ecosystem, right? So that data architecture now is where our focus is. And that's using this open standard, building on the foundation of the open standard called Data Distribution Service, or DDS. So just real quick, what is that? So it's a standard from the Object Management Group that's focused on providing real-time communication. I have to go back one slide, and let me just show you the full stack picture. Second, okay. So now think of, at the lowest level you see the physical bits, right? This is like the actual hardware signaling that is happening, right? So you can think of, then the link layer, this is, the bits which are represented by signals being collected into frames. That's the link layer. The network layer is then those frames are collected into packets, and you are able to exchange packets. And then you've got the transport layer, which is kind of starting to get interesting. So if you are familiar with IP networks, you can think of that as UDP or TCP. And really what those sort of communication protocols allow you to do is take a vector of bytes, right? You can say, okay, I have this sequence or vector of bytes, and I can send it, right? But then to be able to use that information, you have to understand what those bytes mean, right? I'm sure you're familiar with sensors, for example, like LiDAR interfaces, where the vendor, the supplier comes up with their own sort of packing of those bytes. And now you have to integrate that. And to do that, you have to read the manifest, figure out how to decode that, do it correctly, and then that's how that interface works. And if you make a change or the vendor decides to update kind of in the next version, your software has to update, right? So it's very brittle and goes back to that picture, that spaghetti, right? That cascading effect. And so that level of technical interop isn't enough, right? You need the next level, which is called the framework layer in this document. And that's the syntactic interoperability. And that syntactic interoperability about being able to not only get a vector of bytes, but now being able to understand and interpret that unambiguously. Being able to say, okay, I actually understand that this packet has this structure, right? It has, if you are a programmer, think in terms of C or C++ structures, which all of you, I'm sure, okay, this has these fields. Okay, this is X, Y, Z, this is speed, this is power, this is, and it could be variable length, single length. It could be as complex as, LiDAR point clouds, or as simple as, just motor control. Okay, and that ability allows us now for LiDAR sensor in that example, if the LiDAR manufacturer updates their interface behind, the LiDAR interface that we define, we don't have to modify, our side of the software, right? It should still work, right? So we can take that update. Just like, my CarPlay worked, even though my phone probably had different updates than when the CarPlay was implemented on the Wrangler, right? So it works, right? So that's the idea. But that alone isn't sufficient. You also have to have some common semantics. So you need to be able to also say, okay, I understand what the structure is. It's unambiguous, and this standard gives me the ability to understand that. It also gives me the ability to understand what the behavior is in terms of how that data is communicated, but also what the meaning is of those fields in that structure, right? So that's the semantics part. That comes from the data models, right? So the standard, the DDS standard, this is really not just, it's a family of specifications, really. If you start digging into it, it's about more than a dozen different specification documents. It's been around since 2004. It's quite widely used in many other industries. It's been adopted in, as a network binding in AUTOSAR adaptive. I think that happened in 2018. And then I think as of last year, it was added to AUTOSAR Classic for the RTE port. So now you can start to have DDS as a network binding in the RTE. It's also used by open source projects like ROS as the underlying communication, if you're familiar with that. So it's a standard that shows up in many places. But fundamentally, what does that standard provide? And it provides a number of core functions. And fundamentally, one of the core functions is the ability to manage data and model data, right? So at the core of this, and I'm going to talk a little bit here about the yellow part, which is the framework layer, is the ability to model data objects or data resources, right? The ability to say, here's what that data object that has this structure and behavior looks like, right? And that data object now can have, so it's a way of addressing it. So this is how I identify it, not by the IP address, but by the identity of the data itself, right? So it's a data-based
identification so that semantically your applications are not coupled to where something is running, but it's really just focusing on the data, right? A data type system, so that you can define a rich range of data types, data structures, ability to manage life cycle of data. Think CRUD. CRUD stands for create, read, update, delete. So being able to manage the life cycle of data objects, think like, you might have object detections, and you might say, okay, this is something I've identified, it got created, and then it has moved away from my field of view, and so I've deleted it, right? So objects come and go, for example. That's one simple way of thinking about it, but there are many other ways in which you can apply that idea. State management, being able to say, okay, how much history and how much sort of, do I keep, being able to configure all of that through quality of service in terms of data flows, being able to also configure security if you need to, being able to specify security in terms of very fine-grained who can read and write certain data objects, being able to provide governance around that, and then being able to interact with those data objects in terms of different type of interaction patterns we typically see, right? For example, publish subscribe, very common, but also request reply. And then, but to be able to use that, you need to have discovery, right? Who is running what where, and what's available now, and what's now become available as maybe you switch one gear to the other, or you increase the speed to the next sort of level, and you are kicking in some other additional processing and functions, right? And how do you handle exceptions when maybe something reboots or something fails, or you have to switch over to a backup, right? So being able to handle exceptions. And then, of course, having standardized APIs to interact with it, and being able to have standardized wire protocols, right? So the wire protocol is also defined by the standard. So basically, the standard is, if I were to highlight sort of three key aspects of the standard, is defining a standardized wire protocol, which is, if you put in a protocol analyzer like Wireshark, you'll see a standardized description that anybody can recognize. Number two, a standardized vocabulary for modeling data in terms of data types and behaviors. And then number three, standardized APIs in different programming languages, including C++ and others. And then this is what the RSR binding brings up on. Right. So what you then get is, in terms of connecting the software components so that they are able to talk to each other, the ability to connect them. And this is kind of a software component that is your application logic, which is really where your function happens, right? Your functional piece of the software component that's using a data model that you've defined, or we have defined as a community, as an industry, because oftentimes this is non-differentiating. This is like the interface, like the CarPlay interface, right? And then the standard DDS API, which can then implement the data model. And the data bus is like that sort of middleware that's responsible for enforcing the contract that you specified. That contract is that purple box that you see, which is what I call the data interface. And that data interface is saying, here's the data, here's what you read, here's what you write, here's the quality of service, and then go ahead and enforce it. And then the data bus is responsible for getting the right data in the right place at the right time. And that protocol is standardized. So now this software component could be running on any type of compute platform. It could be running in a SOAFI container. It could be, if the data model is standardized, it could be running with an AUTOSAR binding between the application logic. So it could be an AUTOSAR application. If there was a Covisa interface you wanted to support, you would then create a bridge to the common data model, and then you would make that available as well. And all of this is enabled by that common wire protocol, of course, and then the data model that we agreed on as an industry, right? So again, we don't have to sort of expose all the bits and pieces because people often want to put also differentiating pieces of the data model, but then a common baseline data model that is really sort of
how many ways can you describe a LiDAR or a radar, for example, as you're asking? I mean, there's certain basic things that every LiDAR and radar has, and there are differentiating parts, and there are ways to define data models using the DDS vernacular and the vocabulary such that you have differentiating parts and non-differentiating parts, right? So there is a common baseline model, and there's an extensible type system, for example, so that you can then tailor things to sort of the specific use cases, and you can have functionality that can cover a range, right? So that's the idea. That's the idea of one data model, many different programming languages, many different actually programming APIs potentially, many different platforms in terms of compute platforms, and many different type of networks as well. And why that's important? Why is many languages important? Well, if you are thinking of the continuous DevOps cycle, then you have to think about, my developers want to use Python for a quick test, right? Everything doesn't need to be in C++ and fully sort of compliant to ASPICE, right? Of course, you will need that for certain components, but for certain other things, you can have a much faster process. So you have to sort of allow for that space, and having a standard that gives you that range is important, right? Being able to have different language bindings, being able to have support for tools, or things that sort of you can just get from open source just to get something prototype like ROS, and then being able to also use tool environments like MATLAB, which you might be using in the development phases, or using things like LabVIEW during test phases. Being able to bring all of that in around that common data model that's running on that common data bus based on the DDS standard becomes very critical, right? So you want to be able to support kind of the way in which developers are working, so that you can have that time on your side, because already we are solving a complex problem. All right, so then what we are doing is essentially focusing on common pieces of the data model in the AVCC, and focusing on defining the data model in terms of data types, QS profiles, and defining a common data model repo, so that you can have many differentiated software system architectures, and then we can realize that vision of the software ecosystem that's composable, modular, and reusable. All right, so so if you think about where we are in the industry today, if you're following some of the work in this different consortia and standards group, the OMG DDS consortia, or software development organization, and they do things like UML and others as well, that many people use to use any SysML or UML tools. That's also from OMG. That's where that standard comes from. AVCC, we are focusing on then defining the data model piece, which is the common non-differentiating piece. AutoSAR gives you the AutoSAR RCOM in the adaptive side, the RTE interfaces on the classic side that can use the data model and the DDS. Their COVISA is defining a taxonomy for vehicles, and they allow you to define kind of the external view of the vehicle, and you can map that into the standards group, into that common data model. And then, of course, the SOP is defining that ecosystem for portability. And so you can run kind of bare metal, you can run operating system or in a container, and leverage the orchestration as well, and be able to support cloud native development. So you have that full DevOps. So that's kind of a view. We, as a company, are actually engaged in the standards efforts in all of those organizations. So, if you have a particular interest, I'm happy to talk more with people. Okay, so that report is available. I won't go too much into it, but then briefly talk about data-oriented architecture and really what that is, right? Because that's kind of one of the core principles of the recommendation, right? So what is data-oriented architecture and why that's important? And really, it's about building software system architectures that are composed of loosely coupled modular software components. Now that we know what standards are available to support it, let's go back to the concept and understand what that concept really is, why it is so powerful, and why having standards that support it natively is a critical piece to solving the problem. I think as a concept, you'll understand it, but knowing that there are standards to do it effectively puts the whole story together and brings it to life. So the problem with that first approach, where everybody was talking to everybody and it was tightly coupled, was that each software component was kind of aware of the other one, just like that LiDAR interface that you have to understand the packet, right? So if there's a change, it impacts your software component. That's not what we want to do, right? What we want to do is this, right? You want the software components to essentially have a declarative data interface. This is the data I offer. I don't really care who needs it, right? Do what you want with it. This is my standardized interface of how I offer data, right? And if I need data, this is the data I need. This is what I'm requesting from whoever can provide it to me. And I don't care, right? And then the way I operate is I say, well, when my inputs change, I act. And when I act, I change my outputs. I update the data in the data space. So now I have a shared data space where I am simply watching the data space, watching the changes in that data space. And as those happen, I do my thing and I make the update, the data space changes, right? And that's really the idea behind data-oriented architecture. So it's a simple idea. It's a very powerful idea. That's what we want to do. And we see this very effectively applied in many different industries, right? And everybody has heard of databases. We use it all the time. Nobody questions it. And it's the idea of a database, right? It's a storage framework. It's a data-centric storage framework. It's about data at rest, and it allows you to query anything that happened in the past, right? And search and so on. The idea of applying data centricity to data in motion, meaning data changing in real time, is the idea of a data bus. And the data bus is about data-centric filtering of future data, the data that is yet to come. And this is through those declarative interfaces. You are essentially specifying declaratively what you're offering and what you're requesting. And then you rely on the data bus, and think of that as a middleware, as the broker, which is enforcing all of those requirements and getting the right data in the right place at the right time, right? And that middleware, in the case of DDS, the standards are designed in such a way that there is no centralized broker. There is no sort of another process you have to run. It's really just like the TCP/IP library, a library that links into your software application. So your data bus moves to wherever your software components are and expands in contrast to wherever you need to run. Okay, so then we bring that idea to a diagram like this, which has got arrows and lines going everywhere. And then we say, well, can we then slice it in the right places and build those data interfaces, right? And that's really what we are focusing on, so that we can then define those purple data interfaces where those software components interact. And then the data bus takes care of getting the right data in the right place at the right time, right? And then this now allows us to have multiple data buses, even a hierarchy of data buses with the right gateway. So you can also control what goes between different domains, what goes between sort of, different parts, you can have data buses for different levels of, there are many ways to slice it, but that core idea can be applied in many ways. I'm just showing one. And then of course, as the software system needs to change, expand, update, evolve, you can add new functionality because the interface is around the data. And we have shifted that sort of spaghetti of complexity into the data bus, and the data bus is responsible for getting the right data in the right place at the right time. We are just simply adding new things with interfaces that just simply work, right? It's just like my CarPlay. Okay, so this is order N now, it scales beautifully. It gives us loose coupling, it's easy to evolve, it makes it easy to use components. And that's how we make software-defined vehicles real. Right, so we can think of DVS as a standard, that's the software wiring, and gives us a way of managing data flows. I think we're getting tight on time, so I'm going to sort of move through this quickly and we can talk more about this. So data flows are the software wiring, and you can, and we talk about this in detail in the report.
And you can think of them as different types of sort of flows that go through the system, right? From LiDARs, GPS, flying cloud, they have different sizes, shapes, forms, requirements in terms of behavior, right, and structure and so on. DDS is giving us a very rich vernacular, and that's what we are using to define a data model, which allows us to specify the structure and behavior. And there are standard ways of capturing that using DDS IDL and DDS XML. So we can formally create those artifacts, check them into a repository, and then have that common data model repository. And once we have that, then we can have software components that can write to the DDS interfaces. What we're standardizing on is the communication protocol and the programming interface. And then, of course, if you have different APIs that already exist, because software was designed to a different API, we can create bindings to that common data model. This is how adaptive AUTOSAR works, to create a DDS binding for adaptive AUTOSAR. And that's part of the AUTOSAR standards. It's one of the specification documents, actually multiple specification documents of the AUTOSAR standards. And if there are other sort of components that talk other protocols and models, we can create the gateways to do this, right? And this allows us to put all of this together. So really, going back to zonal, and this is what we want to create. I kind of put a cartoon of the hardware side of things here next to this picture. You've got the vehicle compute. Think of that as a centralized compute. Of course, you can have multiple of those. I just put one there. Multiple zones, and of course, multiple buses on those zones as well, connecting to other sort of ECUs, right? So that's fairly typical, very similar to the diagram Partha had earlier. Now, looking at the software view of that hardware piece, what does that look like in this data-oriented architecture, right? So that software component has, is on the vehicle compute. You've got software components, zonal compute, and those software components essentially are, giving you the I/O to whatever needs to happen on the zones. And of course, you might have multiple domains. So you might have different software components for different domains or different functions. And again, many ways you can slice it. Of course, this expands as well. Because the contracts are around the data, it's data-oriented. Now we don't have to worry about tight coupling, right? We can just add software components where they belong. We can even decide to move them, between the central and zonal, depending on how we decide to cut our functionality. And then, of course, this scales out horizontally very nicely, right? We can add more zonal compute. And, really what we are defining is data interfaces. And then now this allows us to build incrementally. So we can add software components, we can have prototype components, we can have production components, we can mix and match. And that's a data-oriented software system. We can define different ways in which we can deploy, right? So this works in, multi-core hypervisor environments, right? So you can have things deployed bare metal, you can have things deployed in Graviton or, x86, x64. Cloud computing nodes, you can mix and match. You can have test environments in the cloud. You can bring the same thing on bare metal. You can mix and match, right? And you can integrate fast, right? You can build around, the data interfaces. You can add sort of new, data buses here. You can add new functions. You can connect them. You can evolve. So again, it works out nicely. So I think that's kind of where I'm going to leave you with, and I'm going to kind of put this picture up, which is showing an autonomous driving example. I don't think I have time to go into detail, but you can kind of now imagine how all those different pieces might come together for, autonomous driving function or ADAS and AD function, where you've got a lot of perception, situational awareness, planning, all of those things. And then maybe you would connect that back to the back end, to the cloud, right? And then now you've got a fully end-to-end, fully, shift left and shift right, as we like to say, the full DevOps piece there, where you are leveraging this approach for development, and then for delivery, and then for operation, right? So that's all I had, and I have probably been a little bit over time, but we can talk more, and I'm happy to connect. So thank you very much.
Thank you, Rajive. Yes, definitely. This is tip of the iceberg on everything that the software portability working group covers. And to go into more details on all of the other working groups in addition to software portability, I'm happy to welcome Stephen Miller, who is our AVCC technical chair, to the stage.
Sarah, and I'm going to need all of you to get out your phone because this is going to be an interactive session using our Slido polling. So you advance your slides and you can actually just the QR code. So go ahead and point your phone at the screen. It'll be an anonymous polling. You'll get to see the results as it happens. It's just kind of for fun, getting us thinking about some of these topics. I also know I'm the last speaker before lunch. We're running a little bit tight on schedule, so I'm going to try to rush through it to get us to break early, but of course, happy to answer and have that deeper discussion. So let me start here. This is, hopefully you've seen this first question. What's one word that explains why I was not able to get driven here today in my autonomous car that I thought I would be maybe 10 years ago? So go ahead and type your word in, and we'll just keep going from there. Well, the context of the talk really is talking about what are the technical working groups that we're doing here in AVCC. And what I want to talk first about is what the work we're doing in the benchmarking working group, and then also talk and highlight a little bit what are some of the things we'll be discussing in the afternoon sessions. So those aren't plenary talks, those are working group times. But for any of you that are here at this event, you're welcome to join us during those working group discussions. It's much more informal, interactive. And as we mentioned, there's these technical reports that come out of that are shared with the industry. And hopefully you can all see the results as well for what we're seeing. We'll go ahead and move on to the next question. And that one is, what's the required TOPS resources for an automotive level 2+ hands-free ADAS SoC? Because really right-sizing the compute is such an important, an important problem for the OEMs, because if you overspec it, it's, costs hundreds of dollars. And of course, if you underspec it, you're never going to add new value over time, or it's not going to perform where it needs to. And so the point of the benchmarking is to help the industry answer that question and answer it in a way that is actually consistent between suppliers and between OEMs. So here we see this model where, as opposed to just everyone send me your specs or your TOPS number, say TOPS lie, let's actually get a benchmark number. So this is a really great collaboration AVCC is doing with ML Commons. We're making ML Perf Automotive. We had a proof of concept, MVP as we call it, that was already produced. So we took an existing model that's quite common, ResNet, but then we added 8 megapixel front camera data, because that's really where we're seeing the front camera resolution at. And then in addition, we've created this framework for running the benchmark, and anyone that becomes part of this, they can then run that benchmark and report those results. Tier 1s, OEMs can really help also define what are those requirements. That work is ongoing. We expect our actually version 1 of the full benchmark to come out in Q1. And that one, we're adding a lot more models as well, of course. So we're not just stopping at ResNet, and of course that will just continue to grow over time. We're looking at real world data, adding radar data as well. So so that's a weekly meeting that occurs. Contact me and I can tell you how to get involved with that. And if we look at the survey results, I guess we need somewhere between 50 and 100 TOPS for level 2+, at least by a third of us. So it's a little more question. Maybe you need a lot more.
If you talk to SoC companies, they will make it even more.
Yeah, so now we know who is answering.
No, that's not true. We want less. We want to be able to do.
Yeah, that is
It's
true.
a great question.
Yeah.
Define L2+. You don't have to do it now.
Yeah. No, that's maybe a harder question, so we'll skip that. But let's go to the next question. which was how much time do you think it would take to develop a new level 3 capable SoC from scratch, okay? But the reason I put that with here is we're starting a new work group on pre-silicon benchmarking or pre-silicon benchmarking best practices. So that group is really just getting kicked off at this meeting. That will be a discussion right after lunch in this room as part of benchmarking. And so we'll be starting to define, okay, what does that need to look like? So again, you're very welcome to join that. The goal here is to develop a technical report. What are the best practices for pre-silicon benchmarking? How do we shift left the development? And since I'm not an SoC guy, I'm just gonna make a guess.
But when you say from scratch, don't mean including the processing core architecture.
You don't have to, we'll pick up the lifeline, something like ARM, or yeah, we can use IT that's out there.
Okay.
You can just speak IP from ARM.
If you use our computer.
At T0, is everything defined?
So what I wanted to avoid was, someone actually, okay, I'm just gonna add this one level and call it level 3. But, I mean, let me put it this way. If you were forming a startup company and your first product was going to be a level 3 SoC, how long would it take? Maybe that's a better way to say it. Right, I'll give you a few more seconds to answer that. Okay. Now we're going to go on to the next question. This one is, what is the power needed to process GPT-4 in real time? This is the energy question. This one is looking as we look to expand benchmarking into system level benchmarking. So the work we're doing with MLPerf is, with ML Commons is specifically on that machine learning, the DNNs, so that part of the compute element. But that may not in the end be the bottleneck for a full system. So what we're transitioning to within AVCC is saying, okay, let's define that system benchmark. So this will start after the pre-silicon one. I think it'll be after the break, after the afternoon break. We'll start defining what we mean by system. What are the additional workloads? We'll continue that discussion into the Wednesday afternoon session. We will look at things even like infotainment, or what if there is large language model for the HMI aspect. Really, what's that full compute load that we could be looking at? And then additionally, foundation models. That's of course, yeah, I mean, it's in automotive already and coming to automotive, I would say. And so that's a really critical topic as well. So we're going to be deep diving into that as well. Okay, yes, a lot of power, maybe more power than your electric vehicle wants for GPT-4. Okay, software portability. Here the next question is what percentage of ADAS software will be written by AI in 2030? So maybe it's all written for us and we reduce the cost that way. Rajive just really gave a nice talk on software portability and what we've done for that. The discussion this afternoon will continue on that data models piece. If we can really plug all the software together in an interoperable way, it'll help it also over the lifetime of the vehicle, okay? The way I think about it is, OEM had the problem of how do they make money? How do you add features to the vehicle over time? And how do you save money? How do we reduce the development cost? And the software portability is a big piece of that. The survey results, right? Well, if you didn't have to type the characters, I'll start with that. This is interesting. So we think most people think somewhere around 60% or more. Interesting. Okay.
So Stephen is already creating the hype curve now.
All right. So another activity in this area of it kind of came out of the software portability, and Elizabeth referenced it earlier, but it's really, as we think again about, okay, we're going to make this big invest in all this software in the vehicle, then you need to start carrying that over time. But you need to port to new, compute architectures over time. And so what's the total cost of ownership of these systems? It's not just what's the silicon, what's the hardware with the cooling. It's really the software can drive a lot of that, and also a lot of the time as well. And so the idea here is looking at the total cost of ownership, and we said we want a very specific question for this report, which is, what are the pain points or the cost drivers for porting software to new compute platforms? And we had an industry survey that opened up recently. I'll show you the link for that in a second. And I really ask you to fill out that survey. I think it might take 15 minutes, but just give some thought to that. You'll see the QR code for that in a second. In this context here for our survey today, what would you expect to pay for an automotive grade 100 TOPS SoC? And again, it's sort of a sliding scale there. So.
You guys clearly are not part of your purchasing department.
Yeah, we heard AMD is selling same SoC for $50, right? We'll order in bulk.
Yeah.
All right, so yeah, every star is a $50 edition. So somewhere around, I see a peak around $250 and another peak around $500 or higher. So interesting, good. All right, I'm going to flash up here. This is the survey. If you open this up, maybe open another tab. But this is the survey that we would like you to fill out for total cost of ownership. So we started promoting an industry. We're looking to get as much input as we can. And then what we're going to do with this survey is take the results, we'll compile them in the technical report. Part of the survey is also like what are some steps that can be done to reduce that total cost. What's some feedback? Then that best practices would also be included in the report, and that report would be available. We think it will help the industry, right? Because if there's areas that are really some of the pain points, those are clearly identified, and then we can invest in those. Right. So back to our other survey. Now we're going to talk about AI cybersecurity. So driving in today, I hear on the radio the Nobel Prize in Physics 2024 is given to AI, Jeffrey Hinton and John Hopfield. So we all know AI is here. It's part of the autonomous vehicle. It's going to be part of infotainment. It's only going to increase. So the security and the safety aspects of that are going to only be magnified. This is also a new working group in AVCC. Jonathan Petit over here is visiting in person also to lead the discussion. He's starting the group that is also meeting today right after lunch is one of our working groups. So we'll be working on defining the scope of that. In the context of AI, the question I had here, hopefully you've seen it, the rank the potential impact of AI relative to the others. So you can kind of move them all around and figure out where they should go. I've heard, I think on the radio today, Jeffrey Hinton said it was as big as the Industrial Revolution, but of course, we want to see what your answer is. In a second, I will do the same. Just for interest, my background is actually in particle physics, so I was around at the birth of the World Wide Web. I wasn't at CERN, but I heard about it very early on. None of us in the room, all PhDs or wannabe PhDs, had any idea what we were just seeing and where it was going to go. So, all right, so we see. I'll give it a minute for a few more entries.
They're all basically equal.
Yeah, and one was supposed to be the highest rank, by the way. I don't know if I specified that. Hopefully you got that, but right. Okay, interesting. So right now I'm seeing AI pretty low in terms of, and so maybe the hype that is the biggest thing since fire is overhyped. Someone mentioned the other day, well, the AI chatbots, I mean, these large language models, if they've already been trained on all the available human knowledge, then they've hit their plateau. Because there's no more knowledge right now to train them on. And so there's some other inflection point that might be needed.
And maybe if you have a room full of software people, have different answers.
All right, yes, that would be an interesting correlation as well. All right, so in any case, we do have the working group on AI because we do want it to be safe and secure for everyone. And then finally, chiplets. We had a really great discussion on chiplets this morning. And there's a number of organizations that are addressing chiplets, obviously the physical interconnect layer, how you make it robust, really being handled well by a lot of organizations. So at AVCC, we don't want to duplicate any of that work. What we want to do is find where we can contribute, probably more in that software, maybe system requirement space to help this ecosystem develop. It's really for that to be successful, as we were, hearing, you need an ecosystem where things can come together in a reliable way, and where those costs can both come down is the same time that the performance is going way up. So in this case, I've been in discussion with a number of people about exactly what that might look like. Please come and talk to me. If you have a specific area, especially, we're looking for someone to lead that working group. So that's obviously a very relevant topic. And here our last question is, what are the enablers for a chiplet ecosystem? So we see, you can see in the word cloud a number of different things, collaboration and standards, of course, sit there pretty heavily. Standardized interconnect and standardization, kind of all the same thing. So that one we don't have a working group on, but again, talk to me about your interest in that area. Just in closing, two things. One is I really want to thank the chairs of the working groups. They've done a tremendous job. It's really exciting and fun to work with these group of individuals. I haven't listed everyone participating in the working groups, but just a lot of good energy and ideas that make working is part of AVCC. A lot of fun. There's a lot of things I learned at AVCC that connect to what I do at Bosch. And vice versa. It's very helpful. And then finally here, just the last slide, here's the schedule of events for today and tomorrow for the working group time.
Thank you, Stephen. I really appreciate it. All right, and with that, we're going to wrap the morning session so that the conference part is over, and we're going to move into working groups this afternoon. So quick things, we are serving lunch on the right-hand side, my right-hand side of the room here. And there's a number of different options, and the beverages continue to be on the left. If anybody needs anything or has any dietary restrictions, please just let us know and we'll guide you through. As Stephen mentioned, this afternoon, we do have the breakout working groups. Benchmarking is going to be in here. Software portability and cybersecurity are across the hall. And when it comes time to find our way over there, just let us know, and we'll be out there and we will guide you across, because there's a badge area and it's a little confusing. So once you do it the first time, you'll be great. But we just don't want anybody to get lost in these little maze of hallways here. We're going to sign off to the online folks. One note is that while we're going through all of the presentations, we haven't had a whole lot of time for Q&A at the end of the speakers. We've had such great material, we haven't wanted to cut it off so that we could open it up to Q&A. But especially online, the questions have been coming, and we're not ignoring them, I promise. So what we've been doing, and Mackenzie's been collecting them, we are going to work with the speakers to get your questions answered and create a collaborative environment where we can continue the conversation, whether it's blog posts or a webinar or an additional opportunity to have that. So don't stop sending the questions. They're really, really important. Just that we don't have time in the limited schedule that we have, we will get to it. So with that, enjoy your lunch and we will see you back at the working groups around 1 o'clock. Thanks.
Oh, it's not. It's-